If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The vast expanse of the cosmos is a stage where creation and destruction occur in a delicate dance of energy and matter. At the heart of this cosmic ballet lies a fundamental truth. Planets are born from stars. But how do these seemingly disparate entities, one a roaring inferno of nuclear fusion, the other a serene orb of rock or gas, connect? To understand the formation of planets, we must first peer into the heart of the universe, where stars themselves come into existence. It begins in the cold and silent regions of space, within the interstellar medium, a sprawling collection of gas and dust that forms molecular clouds. These clouds, seemingly lifeless, harbor the seeds of entire solar systems. Under the influence of gravity, small disturbances within these clouds trigger a collapse, drawing matter inward. This collapse is neither simple nor uniform. It is a chaotic process where regions of higher density emerge as gravitational wells, pulling in more material. As the molecular cloud condenses, it fragments into clumps. Each clump may eventually form a star, surrounded by a swirling disk of leftover material. This disk, known as the protoplanetary disk, is the nursery for planets. But before diving into its role, let's focus on the star at the center. The collapse of the cloud generates heat, and as the core temperature rises to millions of degrees, nuclear fusion ignites, birthing a star. The energy radiated outward halts further collapse, stabilizing the system and lighting up the surrounding space. This moment of stellar birth is also the genesis of planetary potential. The protoplanetary disk, rich in dust and gas, becomes a hotbed of activity. Here, the journey from scattered particles to fully formed planets begins. But why does this disk form in the first place? The answer lies in the conservation of angular momentum. As the collapsing cloud rotates, it flattens into a disk, concentrating material along a plane around the newborn star. The material within the disk is not uniform. Closer to the star, intense heat vaporizes volatile compounds, leaving behind heavier elements like silicates and metals. Further out, cooler temperatures allow for the formation of icy compounds. This temperature gradient creates zones within the disk that will later define the types of planets that form: rocky terrestrial worlds near the star and gas or ice giants farther out. The story of planetary formation, however, does not begin solely with the star. It is deeply influenced by the violent and dynamic environment of the molecular cloud. Nearby massive stars, born from the same cloud, can unleash powerful winds and radiation, sculpting and compressing the protoplanetary disk. This external interference can either accelerate planet formation or disrupt it entirely. Supernovae, the cataclysmic deaths of massive stars, inject heavy elements into the surrounding medium, enriching the nascent disk with materials critical for planet building. What is remarkable is the universality of this process. From our solar system to the distant systems revealed by powerful telescopes, the interplay between stars and their disks appears to follow a consistent pattern. This insight has transformed our understanding of how worlds like Earth come into being. Observations of young stars, cloaked in their protoplanetary disks, provide a glimpse into this formative stage. Infrared and radio telescopes detect the heat and emissions from these disks, revealing their structure and composition. But a question emerges: what determines whether a disk becomes a planetary system? Not all protoplanetary disks succeed in forming planets. Some are stripped of their material too quickly, while others may lack sufficient mass. The balance between the forces of gravity, radiation, and magnetic fields plays a crucial role. Additionally, the presence of turbulence within the disk can either hinder or enhance the aggregation of particles into larger bodies. As we gaze into the heavens, we see stars as solitary points of light, yet they are anything but alone. Each star carries the potential for planets, moons, and even life. The birth of a star is not merely the ignition of nuclear fusion. It is the spark that sets in motion the creation of entire worlds. Yet, this is only the first chapter in the epic tale of planetary formation. The protoplanetary disk, that shimmering cradle of matter, awaits its turn to shape the next stage of cosmic evolution. The protoplanetary disk is the birthplace of worlds, a swirling expanse of gas and dust encircling a newborn star. Its unassuming appearance belies the complex and chaotic processes unfolding within. This disk is where the journey from scattered cosmic material to fully formed planets begins, and every tiny grain and molecule within it plays a role in crafting a planetary system. To understand this process, we must delve deep into the structure and dynamics of this primordial environment. At first glance, the protoplanetary disk seems like a homogeneous cloud of debris, but closer examination reveals a layered structure. Closest to the star lies the hot zone, where temperatures soar to thousands of degrees Kelvin. Here, the intense heat vaporizes volatile compounds like water, methane, and ammonia, leaving behind heavier elements such as silicates and metals. This region becomes the foundation for terrestrial planets, rocky worlds like Earth and Mars. Further out, in the cooler reaches of the disk, temperatures drop significantly. This area is known as the frost line or snow line, a critical boundary where icy compounds can condense. Beyond this line, gas giants and ice giants like Jupiter and Neptune begin their formation. The frost line plays a crucial role in determining the composition and size of planets. Its position varies depending on the star's luminosity and the disk's density. The gas within the disk, predominantly hydrogen and helium, dominates its mass. However, the tiny dust particles scattered throughout are the true architects of planet formation. These grains, composed of elements forged in the cores of ancient stars, collide and stick together in a process known as accretion. Over time, these collisions lead to the formation of larger aggregates called planetesimals, the building blocks of planets. Yet this process is not as straightforward as it seems. The disk is a turbulent environment, with swirling eddies, shock waves, and magnetic fields creating regions of high and low pressure. These dynamics influence how material moves within the disk, concentrating dust in some areas while dispersing it in others. These pressure traps become critical zones where planetesimals can grow rapidly, overcoming the challenges posed by drag forces that threaten to pull them into the star. One of the greatest mysteries in planetary science is how these small grains manage to grow into kilometer-sized planetesimals. The problem lies in what scientists call the meter barrier. Objects of this size are prone to spiraling into the star due to the effects of drag, making their survival a matter of intense study. Some theories suggest that instabilities within the disk create dense clumps of material that collapse under their own gravity, bypassing this barrier. As planetesimals grow, they begin to influence their surroundings. Their increasing gravity allows them to attract more material, accelerating their growth in a runaway process. In regions rich in gas, these bodies may also gather thick atmospheres, setting the stage for the formation of gas giants. Meanwhile, in the inner disk, where gas is scarce, smaller, rocky planets begin to take shape. The composition of the disk also determines the diversity of planets it can produce. Elements like carbon, oxygen, and silicon play a significant role in shaping planetary characteristics. The relative abundance of these elements varies between disks, influenced by the star's metallicity, a measure of the heavier elements present in the star and its surroundings. Stars with higher metallicity are more likely to form planets, particularly gas giants, as their disks are richer in the materials necessary for core growth. The protoplanetary disk is not a static entity. Over time, it evolves under the influence of the star's radiation and winds. Ultraviolet and X-ray emissions from the star gradually erode the disk, driving away gas and leaving behind a thinner, more diffuse structure. This dissipation marks the end of the planet-forming era, usually within a few million years. However, the remnants of the disk, such as asteroid belts and Kuiper belt-like regions, often persist as a testament to this formative stage. Our understanding of protoplanetary disks has been revolutionized by observations from telescopes like ALMA, which reveal these disks in exquisite detail. Rings, gaps, and spirals within the disks provide clues about the planets taking shape within. These features suggest that planet formation begins much earlier than previously thought, with young disks already showing signs of planet-induced structures. The primordial disk is a crucible of creation, where the raw ingredients of the cosmos are transformed into the intricate architectures of planetary systems. It is a place of constant motion, where gravity, chemistry, and physics converge to sculpt the building blocks of worlds. As we continue to study these disks, we not only uncover the secrets of our own solar system's origins, but also gain insight into the diversity of planets scattered throughout the galaxy. The formation of gas giants, the behemoths of planetary systems, is a tale of cosmic ambition. These colossal planets, composed primarily of hydrogen and helium, dominate their respective domains with immense mass and gravitational influence. Their creation is not only a pivotal chapter in the story of planetary formation, but also one that raises profound questions about the dynamics of the early solar system and beyond. Gas giants like Jupiter and Saturn do not form randomly. Their genesis requires specific conditions within the protoplanetary disk. These conditions must be met within a relatively short time frame, as the gas in the disk disperses within a few million years. The two leading theories for the formation of these giants, core accretion and disk instability, attempt to explain how these massive planets emerge from the chaotic environment of the primordial disk. The most widely accepted model is the core accretion theory. According to this model, the process begins with the formation of a solid core, roughly 10 times the mass of Earth. This core forms through the accumulation of planetesimals in the cooler, outer regions of the disk, beyond the frost line. Here, icy materials and other volatiles are abundant, allowing cores to grow more rapidly than in the inner, rocky regions. Once the core reaches a critical mass, its gravitational pull becomes strong enough to attract and retain a surrounding envelope of gas. This process, known as runaway gas accretion, allows the nascent planet to grow rapidly, potentially reaching hundreds of Earth masses. However, this growth must occur before the disk's gas dissipates, a race against time that places significant constraints on the conditions under which gas giants can form. While core accretion provides a robust framework for understanding gas giant formation, it struggles to explain certain observations, particularly in systems with massive planets located far from their stars. Enter the disk instability model, an alternative theory that proposes a more rapid formation process. In this scenario, gravitational instabilities within the protoplanetary disk create dense clumps of gas and dust. These clumps collapse under their own gravity, forming gas giants directly, bypassing the need for a solid core. Disk instability may be more efficient in disks that are massive, cool, and prone to turbulence. However, it remains a subject of debate among astronomers, as evidence supporting this mechanism is less direct than that for core accretion. It is possible that both processes operate under different conditions, contributing to the diversity of gas giants observed across the galaxy. The growth of gas giants has profound implications for the architecture of planetary systems. These massive planets exert tremendous gravitational influence, capable of shaping the orbits of other bodies in the system. Their formation often triggers a cascade of interactions, leading to the migration of planets from their birthplaces. Planetary migration, in turn, explains the existence of hot Jupiters, gas giants found surprisingly close to their stars, too close for traditional models to account for their formation. Migration occurs through interactions with the surrounding disk or other planets. In the early stages, gas giants can create spiral density waves in the disk, altering their orbits. Over time, this can bring them closer to the star or push them outward, depending on the specific dynamics involved. These movements can disrupt the formation of smaller, rocky planets, creating systems that differ dramatically from our own. The chemical composition of gas giants also offers a window into their formation history. By analyzing their atmospheres, astronomers can infer details about the conditions in the disk where they formed. For instance, the presence of certain heavy elements suggests that these planets accumulated material from regions rich in icy planetesimals. This aligns with the idea that the frost line plays a crucial role in determining the properties of gas giants. Observations of exoplanetary systems reveal an astonishing variety of gas giants, from superjupiters many times the mass of our largest planet to mini-Neptunes with thick atmospheres and smaller cores. This diversity challenges existing models and suggests that the interplay of disk properties, migration, and formation mechanisms produces a wide range of outcomes. The study of gas giants has also shed light on the role of binary star systems and stellar companions in shaping planetary formation. Disks in such environments often exhibit asymmetries and instabilities, which can accelerate or hinder the growth of massive planets. Understanding these dynamics helps refine our models and improve predictions for where gas giants might form in various types of systems. Despite their dominance in size, gas giants often play a supporting role in fostering conditions for habitability in their systems. By shepherding debris and influencing the delivery of water and volatiles to rocky planets, these giants contribute indirectly to the development of life-friendly worlds. In our own solar system, Jupiter's immense gravity acts as both a shield, deflecting comets and asteroids, and a potential source of chaos, perturbing orbits over long timescales. The birth of gas giants is a story of scale and precision. From the tiny dust grains in the primordial disk to the towering masses of hydrogen and helium they become, these planets embody the extremes of planetary formation. Their existence and variety offer clues to the processes that shaped not only our solar system, but also the countless planetary systems scattered across the cosmos. The formation of terrestrial planets, rocky worlds like Earth, Venus, Mars, and Mercury, is a process that unfolds with precision and complexity. Unlike their gas giant counterparts, these planets arise in the inner regions of the protoplanetary disk, where heat and proximity to the star play decisive roles. The story of their genesis is a testament to the resilience of solid matter under the influence of gravity, collisions, and time. In the inner solar system, the protoplanetary disk is a furnace. Temperatures are high enough to vaporize volatile compounds like water, methane, and ammonia, leaving behind a concentrated mix of silicates and metals. These materials become the foundation for terrestrial planets, which are characterized by their solid, rocky surfaces and dense compositions. The process begins with microscopic dust grains composed of silicon, oxygen, iron, and other heavy elements. These grains collide and stick together, forming larger particles in a process known as coagulation. Over thousands of years, these particles grow into pebble-sized aggregates. However, the turbulent environment of the disk creates challenges for growth beyond this stage. Collisions at higher speeds can fragment particles rather than allow them to stick, making the leap from pebbles to larger bodies a critical bottleneck. To overcome these challenges, researchers propose that regions of the disk experience localized pressure maxima, where material concentrates. These sweet spots enable the rapid formation of planetesimals, bodies ranging from a few kilometers to hundreds of kilometers in size. Gravity becomes the driving force at this stage, pulling smaller particles onto these nascent worlds and allowing them to grow through accretion. As planetesimals grow larger, their gravitational influence increases, enabling them to attract more material and merge with other planetesimals. This runaway growth phase produces protoplanets, bodies large enough to dominate their immediate surroundings. In the inner disk, protoplanets are composed primarily of silicates and metals, as lighter, icy materials are scarce or non-existent. The environment of the inner disk is dynamic and often violent. Collisions between protoplanets are frequent, and these impacts play a significant role in shaping the final characteristics of terrestrial planets. For example, the Moon is thought to have formed as a result of a colossal impact between the early Earth and a Mars-sized body, an event that reshaped both worlds and left a lasting mark on our planet's geology and orbital dynamics. The process of forming terrestrial planets is also influenced by the star's activity. Young stars emit intense radiation and winds, which can erode the disk and strip away gas and dust. This process limits the time available for planets to form and imposes constraints on their final sizes and compositions. In some systems, these factors may prevent the formation of terrestrial planets altogether, leaving behind only a barren field of planetesimals and debris. One of the most intriguing aspects of terrestrial planet formation is the delivery of water and other volatiles. While the inner disk is too hot for these compounds to condense, they can be delivered by icy bodies migrating from the outer regions of the disk. In our solar system, this process likely involved comets and asteroids that carried water and organic molecules to the early Earth, setting the stage for the emergence of life. The formation of terrestrial planets is not a uniform process. It is deeply influenced by the specific conditions of the protoplanetary disk. Variations in metallicity, turbulence, and disk density can lead to a wide range of outcomes. Some systems may produce multiple rocky planets, while others yield only a single dominant world. The diversity of terrestrial planets observed in exoplanetary systems underscores the influence of these factors. Another fascinating aspect is the role of giant planets in shaping the formation of rocky worlds. In some systems, gas giants like Jupiter migrate inward, disrupting the disk and scattering planetesimals. This process, known as the Grand Tack hypothesis, may explain why Mars is much smaller than Earth and Venus. The gravitational influence of gas giants can also protect the inner disk from excessive bombardment, creating a more stable environment for planet formation. The study of terrestrial planets extends beyond their formation to their evolution. As these planets mature, they undergo processes such as differentiation, where heavier elements sink to form a core, while lighter materials rise to create a mantle and crust. This internal structure has profound implications for a planet's geology, magnetic field, and potential for habitability. Observations of exoplanetary systems have revealed a surprising variety of rocky worlds, from super-Earths with thick atmospheres to scorched planets orbiting perilously close to their stars. These discoveries challenge traditional models and suggest that terrestrial planet formation may be more diverse and dynamic than previously thought. For instance, the presence of super-Earths in many systems raises questions about why our solar system lacks such planets, pointing to unique factors in our system's history. The study of terrestrial planet formation is not just an exercise in understanding our cosmic origins. It also informs the search for life beyond Earth. By identifying the conditions under which rocky planets form and acquire the ingredients for life, we can refine our search for habitable worlds. Missions like the James Webb Space Telescope and ground-based observatories continue to uncover new details about these distant rocky realms, bringing us closer to answering one of humanity's oldest questions. Are we alone in the universe? The story of terrestrial planet formation is far from complete, and each new discovery adds another piece to the puzzle. These rocky worlds, born from chaos and forged by collisions, stand as testaments to the remarkable processes that shape the universe. The role of collisions in shaping worlds is a cornerstone of planetary formation and evolution. From the earliest moments of planetesimal formation to the violent impacts that sculpt mature planets, these cataclysmic events define the very essence of planetary systems. Collisions are not merely destructive. They are creative forces that drive diversity, determine planetary characteristics, and, in some cases, even set the stage for life itself. In the early stages of planetary formation, collisions are frequent and fundamental. Within the protoplanetary disk, dust grains collide and stick together, forming larger aggregates in a process driven by electrostatic forces and weak gravitational interactions. Over time, these aggregates grow into kilometer-sized planetesimals. However, as these bodies increase in size and mass, the nature of their collisions changes. Gravity becomes the dominant force, leading to more energetic and impactful encounters. Planetesimals collide to form protoplanets, the precursors of full-fledged planets. These collisions, while often violent, allow material to accumulate, enabling protoplanets to grow. The energy released during these impacts heats the material, causing partial melting and differentiation. This process separates heavy elements like iron, which sink to form a core, from lighter silicates that rise to create a mantle and crust. Without these early collisions, planets would lack the layered internal structures that define them. However, not all collisions are constructive. High-velocity impacts can shatter bodies rather than allow them to merge. These destructive collisions create a cascade of debris, contributing to the formation of asteroid belts and planetary rings. The balance between constructive and destructive collisions depends on factors such as the relative velocities of the colliding bodies, their sizes, and the gravitational influence of nearby planets. One of the most profound examples of collision-driven creativity is the formation of the Moon. The leading hypothesis suggests that a Mars-sized protoplanet, often referred to as Theia, collided with the early Earth. The impact was catastrophic, ejecting a massive amount of debris into orbit around Earth. This debris eventually coalesced to form the Moon. This event not only gave Earth its satellite but also played a critical role in stabilizing the planet's axial tilt, influencing its climate and seasons. Collisions also influenced the delivery of essential materials to planets. During the late heavy bombardment, a period of intense impacts in the solar system's history, comets and asteroids bombarded the inner planets. These icy and rocky bodies carried water, organic molecules, and other volatiles, delivering the building blocks for life to Earth and possibly other worlds. Such impacts may have also been responsible for creating temporary warm environments on otherwise frozen planets, sparking chemical reactions that lead to prebiotic chemistry. The scars of these ancient collisions are visible across the solar system. Mercury's surface is heavily cratered, a testament to its violent past. The enormous Caloris Basin, one of the largest impact craters in the solar system, hints at the scale of these collisions. Similarly, the asteroid Vesta reveals a giant impact basin at its south pole, where a collision stripped away much of its crust and mantle. Beyond shaping individual planets, collisions also play a role in determining the architecture of planetary systems. When giant planets form and migrate, their gravitational interactions can destabilize the orbits of smaller bodies, triggering a period of intense collisions. This process, known as orbital clearing, helps define the final arrangement of planets in a system. It also explains why some systems lack small rocky planets, as these worlds may have been ejected or destroyed in the chaos of early system evolution. Collisions are not confined to the early stages of planetary formation. Even mature planetary systems experience impacts, as evidenced by the craters on the Moon, Mars, and Earth. These later collisions, while less frequent, can have dramatic consequences. The Chicxulub impact, which occurred approximately 66 million years ago, caused a mass extinction that wiped out the dinosaurs and reshaped Earth's biosphere. This event highlights the dual nature of collisions, destructive in the short term, but potentially transformative in the long run. In some cases, collisions can even lead to the formation of entirely new celestial features. The rings of Saturn, for example, may have formed from the debris of a shattered moon or comet. Similarly, irregular moons around planets like Jupiter and Neptune may be captured remnants of past collisions. The role of collisions extends beyond our solar system. Observations of distant planetary systems reveal disks of debris, often the result of ongoing collisions between planetesimals and protoplanets. These debris disks provide a snapshot of planetary formation in action, offering clues about the processes that shaped our own solar system. Collisions are also key to understanding the atmospheres of planets. Impacts can strip away atmospheres, as may have happened on Mars, or deliver gases that contribute to the development of an atmosphere, as seen on Earth. They can even trigger volcanic activity by creating enough heat to melt subsurface materials, releasing gases and altering a planet's surface. As we continue to study collisions, new technologies and observations offer deeper insights. High-resolution simulations allow scientists to model the outcomes of impacts, from the initial collision dynamics to the long-term effects on planetary evolution. Observations from missions like the Lunar Reconnaissance Orbiter and the James Webb Space Telescope provide direct evidence of impact features and their consequences on celestial bodies. Collisions are more than random events. They are the architects of worlds. From shaping planetary surfaces to influencing atmospheres and delivering the ingredients for life, these dramatic encounters play a central role in the cosmic narrative. The echoes of these impacts resonate across the solar system and beyond, reminding us that creation and destruction are intertwined in the universe's grand design. Planetary migration is one of the most dynamic and transformative processes in the evolution of planetary systems. Far from being fixed in place, planets often shift from their birth locations, carving new paths through their protoplanetary disks and reshaping the architecture of their systems. This phenomenon explains many of the anomalies observed in exoplanetary systems and provides new insights into the early history of our own solar system. In the chaotic environment of the protoplanetary disk, planetary migration begins almost as soon as planets start forming. The gas and dust within the disk create a gravitational tug on nascent planets, which in turn perturb the disk material. This mutual interaction initiates migration, causing planets to move inward or outward depending on the specifics of the forces at play. There are several types of planetary migration, each influenced by the size of the planet and the properties of the disk. Type 1 migration affects smaller planets, such as Earth-sized or smaller bodies, which interact with the disk through subtle gravitational forces. These interactions create density waves in the gas, forming regions of higher and lower pressure. Depending on the relative strength of these waves, the planet may move inward toward the star or outward toward the cooler edges of the disk. For larger planets, Type 2 migration comes into play. As massive planets like Jupiter or Saturn form, they clear gaps in the disk by gravitationally sweeping away material in their vicinity. The remaining gas in the disk continues to exert forces on the planet, causing it to migrate. This process is slower than Type 1 migration, but can result in significant shifts over the lifetime of the disk. Another intriguing phenomenon is Type 3 migration, which occurs when planets interact with dense streams of gas in the disk. This type of migration can happen rapidly, causing planets to shift their orbits in relatively short periods. While less common, it may explain some of the more extreme exoplanetary configurations observed. Migration can have profound consequences for the architecture of planetary systems. One of the most striking examples is the existence of hot Jupiters, gas giants that orbit perilously close to their stars. These planets could not have formed in their current locations, as the high temperatures near the star would have prevented the accumulation of gas. Instead, they likely formed further out in the disk and migrated inward. This inward journey may have disrupted the formation of smaller planets, leaving systems with hot Jupiters devoid of terrestrial worlds. In our own solar system, migration played a crucial role in shaping its final structure. The Grand Tack hypothesis proposes that Jupiter initially migrated inward toward the Sun before reversing course and moving outward. This dramatic movement, influenced by interactions with Saturn, disrupted the distribution of material in the inner solar system, explaining the small size of Mars and the absence of super-Earths. It also likely scattered icy bodies inward, delivering water and other volatiles to the inner planets, including Earth. Similarly, the NICE model describes how the migration of the giant planets, Jupiter, Saturn, Uranus, and Neptune, reshaped the outer solar system. As these planets moved, their gravitational interactions destabilized smaller bodies, flinging many into the Kuiper belt and Oort cloud while sending others inward to collide with the terrestrial planets. This period of instability is thought to have caused the Late Heavy Bombardment, a time of intense impacts that left lasting scars on the Moon and other bodies. Planetary migration is not limited to the early stages of system formation. Even mature planetary systems can experience migration under the right conditions. For example, gravitational interactions between planets can cause long-term changes in their orbits. In some cases, this process can lead to orbital resonances, where planets exert regular, periodic gravitational influences on each other. These resonances can stabilize or destabilize orbits, depending on their nature. Migration also has implications for habitability. Planets that migrate inward may move into or out of the habitable zone, the region around a star where conditions are suitable for liquid water. This movement could sterilize potentially life-friendly worlds by exposing them to extreme heat or strip them of their atmospheres. Conversely, migration could bring icy worlds into the habitable zone, melting surface ice and creating conditions for life to develop. The mechanisms driving migration are not entirely understood, and many questions remain. Why do some systems retain stable, widely spaced orbits, while others produce tightly packed configurations? What factors determine whether migration is inward or outward? And how do interactions between planets influence the outcomes of migration? Observations of exoplanetary systems, coupled with advanced simulations, are beginning to provide answers. Exoplanet discoveries have revealed a staggering diversity of planetary systems, many of which bear little resemblance to our own. The prevalence of hot Jupiters, super-Earths, and tightly packed multi-planet systems suggests that migration is a common and influential process. Observations of protoplanetary disks, such as those made by the ALMA Observatory, show gaps, rings, and spirals that hint at the presence of migrating planets shaping their environments. Migration is not just a story of planets moving. It is a tale of entire systems evolving. The interplay between planets, disks, and stars creates a dynamic landscape where worlds are constantly reshaped. Understanding this process sheds light on the formation and evolution of planetary systems, including our own, and provides context for the incredible variety of worlds we observe across the galaxy. Exoplanets, planets orbiting stars beyond our solar system, have transformed our understanding of the universe and our place within it. These distant worlds come in a staggering array of sizes, compositions, and orbital configurations, revealing that the diversity of planetary systems far exceeds the relative simplicity of our own. Each new discovery challenges our models of planet formation and forces us to reconsider what we thought we knew about how worlds are born and evolve. The search for exoplanets began in earnest in the 1990s, when the first definitive detections were made. The discovery of 51 Pegasi b, a gas giant orbiting extremely close to its star, was a watershed moment. This hot Jupiter defied expectations, as existing theories could not explain how such a massive planet could form and remain in such a tight orbit. Since then, advancements in observational techniques and instruments have revealed thousands of exoplanets, each offering new clues about the processes that shape planetary systems. One of the most striking revelations from exoplanet studies is the sheer variety of planetary types. While our solar system features gas giants, terrestrial planets, and icy worlds, exoplanet discoveries have introduced entirely new categories, such as super-Earths and mini-Neptunes. Super-Earths, which are larger than Earth but smaller than Neptune, challenge our understanding of planet formation, as they occupy a mass range not found in our solar system. Similarly, mini-Neptunes are gas-rich planets smaller than Neptune but larger than Earth, raising questions about the diversity of atmospheric and core compositions. These discoveries have also highlighted the importance of planetary migration. Many exoplanetary systems feature tightly packed planets, with orbits far closer to their stars than Mercury is to the sun-hot Jupiters. In particular, demonstrate the dramatic effects of migration, as these gas giants must have formed far from their stars before migrating inward. The prevalence of such planets suggests that migration is a common feature of planetary system evolution, reshaping the orbits and dynamics of entire systems. The diversity of exoplanetary atmospheres has opened new frontiers in our understanding of planetary environments. Using techniques such as transit spectroscopy, astronomers can study the light passing through a planet's atmosphere as it transits its star. This method has revealed the presence of water vapor, carbon dioxide, methane, and other compounds in exoplanetary atmospheres. These findings not only inform us about the chemical processes occurring on distant worlds, but also hint at their potential habitability. One of the most profound questions driving the study of exoplanets is the search for life beyond Earth. While many exoplanets are hostile to life as we know it, a growing number of Earth-sized planets have been discovered in the habitable zones of their stars. The habitable zone, often referred to as the Goldilocks zone, is the region where temperatures allow for liquid water to exist on a planet's surface. Planets like Proxima Centauri b and those in the TRAPPIST-1 system have become prime targets for future observations, as they represent some of the most promising candidates for harboring life. However, habitability is influenced by more than just location. A planet's atmosphere, magnetic field, and geological activity all play critical roles in maintaining conditions suitable for life. For example, Venus lies within the Sun's habitable zone, but is inhospitable due to its runaway greenhouse effect. Conversely, moons like Europa and Enceladus, which lie far outside the Sun's habitable zone, may host subsurface oceans warmed by tidal heating, potentially providing environments where life could thrive. Exoplanet discoveries have also forced astronomers to reconsider the uniqueness of our solar system. While once thought to be a typical example, our system's lack of super-Earths, abundance of stable orbits, and relative distance between planets now appear to be rare features. This uniqueness raises intriguing questions about why our solar system formed the way it did, and whether such configurations are necessary for the development of complex life. Technological advancements have been instrumental in accelerating the pace of exoplanet discoveries. The Kepler Space Telescope revolutionized the field by using the transit method to detect thousands of exoplanets, demonstrating that planets are a common feature of the galaxy. Its successor, the Transiting Exoplanet Survey Satellite TESS, continues this work, focusing on nearby stars to identify exoplanets that can be studied in greater detail. Ground-based observatories and upcoming missions like the James Webb Space Telescope and the European Extremely Large Telescope promise to provide even more detailed observations of exoplanetary atmospheres and compositions. These observations have not only expanded our catalog of exoplanets, but also deepened our understanding of planetary formation. For example, the discovery of planets in binary star systems has revealed the surprising adaptability of planet formation processes. Similarly, the detection of planets around small, dim stars known as red dwarfs suggests that these stars, which make up the majority of stars in the galaxy, may host a vast number of potentially habitable worlds. Exoplanets also serve as laboratories for testing theories about planetary interiors, atmospheres, and magnetic fields. For instance, studying the thermal emissions of hot Jupiters has provided insights into atmospheric circulation and the effects of intense stellar radiation. Observations of rocky exoplanets have begun to hint at their surface compositions and potential for volcanic activity, which could influence their ability to support life. The study of exoplanets is not just about cataloging worlds. It is about understanding the processes that create them. By comparing the properties of exoplanets to those of the planets in our solar system, scientists can refine models of planet formation and evolution. These comparisons reveal the factors that contribute to the diversity of planetary systems, from the influence of stellar metallicity to the role of disk dynamics. As we continue to uncover the secrets of exoplanets, we are reminded of the profound connection between these distant worlds and our own. The processes that shaped Earth and its neighbors are the same forces sculpting exoplanetary systems across the galaxy. Each new discovery not only expands our knowledge of the universe, but also deepens our appreciation for the fragile, intricate chain of events that led to the formation of our home. Super-Earths and mini-Neptunes represent some of the most intriguing and enigmatic categories of exoplanets. These worlds, which occupy a size range between Earth and Neptune, defy the traditional boundaries of planet classification. Their prevalence in exoplanetary systems, paired with their complete absence in our own, challenges existing theories of planetary formation and forces astronomers to rethink the diversity of planetary systems. Super-Earths are generally defined as rocky planets with masses up to 10 times that of Earth. They may be scaled-up versions of our home planet, with thicker atmospheres, greater geological activity, and potentially vast oceans. Mini-Neptunes, on the other hand, are smaller versions of gas giants, with thick hydrogen-helium atmospheres surrounding rocky or icy cores. Despite their similarities in size, these two planet types likely have distinct formation histories and characteristics. One of the great mysteries surrounding super-Earths and mini-Neptunes is why they are so common in other star systems, yet completely absent in our solar system. Observations from the Kepler Space Telescope have shown that many stars host compact systems of these planets, often orbiting close to their stars. This contrasts sharply with our own solar system, where the closest planets are small, rocky worlds, and gas giants occupy the distant reaches. The explanation for this discrepancy likely lies in the formation environment of the protoplanetary disk. Super-Earths and mini-Neptunes may form in regions of the disk where conditions favor the rapid accumulation of material. Their intermediate size suggests that they may have started as rocky cores, similar to terrestrial planets, but then either grew massive enough to attract substantial gaseous envelopes or remained relatively small and rocky. The abundance of these planets in other systems implies that the specific conditions in our solar system, perhaps the influence of Jupiter's migration or the unique distribution of materials in the disk, prevented their formation. Super-Earths, in particular, are fascinating because of their potential for habitability. Their greater mass allows them to retain thicker atmospheres, which can stabilize surface conditions and protect against harmful radiation. If these planets also host magnetic fields generated by active cores, they might offer even greater protection for any potential biospheres. However, their higher gravity and atmospheric pressure could lead to very different surface environments, potentially making them alien in ways we can barely imagine. On the other hand, mini-Neptunes blur the line between terrestrial and gas planets. Their thick atmospheres, composed mainly of hydrogen and helium, create conditions far removed from those of rocky planets. Beneath these gaseous layers, however, may lie solid or liquid surfaces, potentially with high-pressure water oceans. These environments, though unlikely to host life as we know it, raise intriguing possibilities about the diversity of planetary habitats. Understanding the formation of these intermediate planets requires examining their composition and density. Astronomers use techniques such as transit timing variations and radial velocity measurements to estimate their masses and radii. By comparing these properties, scientists can infer their bulk compositions. For instance, a super-Earth with a high density is likely composed predominantly of rock and metal, while a mini-Neptune with a low density suggests a significant gaseous envelope. The boundary between super-Earths and mini-Neptunes is not always clear. Planets with radii around 1.6 times that of Earth tend to have densities indicating a predominantly rocky composition, while those with radii greater than 2.0 Earth radii often exhibit characteristics of mini-Neptunes. This transition likely reflects the point at which a planet's gravity becomes strong enough to retain a significant atmosphere, creating a spectrum rather than a distinct divide between these two categories. The role of stellar type in shaping super-Earth and mini-Neptune populations is another area of active research. These planets are particularly common around M dwarfs, the most abundant type of star in the galaxy. The close-in habitable zones of these cooler stars mean that many of their super-Earths and mini-Neptunes orbit within regions where liquid water could exist. However, the intense stellar flares and radiation from young M dwarfs could strip away atmospheres, complicating the habitability of such planets. Atmospheric escape is a critical factor in determining whether a planet becomes a super-Earth or a mini-Neptune. During their early evolution, planets are bombarded by intense radiation from their stars, which can erode lighter elements from their atmospheres. If a planet starts with a thick, gaseous envelope but loses most of it due to this process, it may be left as a stripped-down rocky super-Earth. Conversely, planets with stronger gravity or those further from their stars may retain their atmospheres, evolving into mini-Neptunes. Recent observations of super-Earth and mini-Neptune atmospheres have begun to shed light on their compositions. Using tools like the Hubble Space Telescope and ground-based observatories, astronomers have detected water vapor, hydrogen, helium, and other elements in these atmospheres. These findings provide clues about the planet's origins and the chemical processes occurring within their environments. Future missions, such as the James Webb Space Telescope, promise to offer even more detailed analyses, potentially revealing the presence of complex molecules or even biosignatures. Super-Earths and mini-Neptunes also serve as natural laboratories for testing theories of planetary formation and evolution. Their existence challenges traditional models, which were developed based on the relatively limited diversity of planets in our solar system. The study of these intermediate worlds forces us to reconsider fundamental questions about the processes that govern the growth of planets, the dynamics of protoplanetary disks, and the interplay of migration and atmospheric evolution. These planets are not merely oddities. They represent the norm in the galaxy. Their abundance suggests that the processes leading to their formation are both efficient and widespread. As we continue to discover and characterize these worlds, we are not only expanding our knowledge of planetary diversity, but also gaining valuable perspectives on our own planet's uniqueness, or lack thereof, in the cosmos. The journey from pebbles to planets is one of the most intricate and fascinating processes in the universe. From tiny grains of cosmic dust to massive worlds capable of hosting life, this transformation unfolds across millions of years in the chaotic environment of a protoplanetary disk. Understanding this process requires peeling back the layers of planetary formation to reveal the subtle interplay of physics, chemistry, and time. At the beginning, the protoplanetary disk is a swirling cloud of gas and dust surrounding a newborn star. Within this disk, the smallest building blocks of planets, microscopic grains of silicate and ice, drift and collide. These grains are the remnants of earlier generations of stars, enriched with heavy elements forged in supernovae. Despite their minuscule size, They contain the raw materials for entire planetary systems. The first step in planetary formation is coagulation, where grains collide and stick together. This process is driven by electrostatic forces, as the tiny particles are charged. Over time, these grains grow into millimeter to centimeter-sized pebbles. While small in scale, this phase is crucial, as it sets the stage for larger structures to emerge. The disk's turbulence, temperature gradients, and chemical composition all influence the rate and efficiency of coagulation. As pebbles accumulate, they form larger aggregates through continued collisions. These centimeter to meter-sized objects face a significant hurdle: the drag exerted by the gas in the disk. This drag causes them to lose angular momentum and spiral inward toward the star. Known as the meter-sized barrier, this phase poses a challenge to planetary formation, as many objects are lost to the star before they can grow larger. To overcome this barrier, researchers propose several mechanisms. One possibility is the formation of pebble clusters in regions of the disk with high pressure or turbulence. These clusters can collapse under their own gravity to form kilometer-sized planetesimals. Another theory involves streaming instabilities, where pebbles concentrate in narrow bands within the disk, triggering rapid gravitational collapse. Both processes offer pathways for small objects to bypass the meter-sized barrier and grow into planetesimals. Once planetesimals form, gravity takes over as the primary force driving growth. These objects collide and merge, creating larger bodies in a process called accretion. This phase is marked by a delicate balance. Collisions must be energetic enough to allow merging, but not so violent as to cause fragmentation. Over time, planetesimals grow into protoplanets, bodies large enough to begin shaping their surroundings. The protoplanet stage is a critical juncture in planetary formation. These objects, ranging from hundreds to thousands of kilometers in diameter, dominate their local regions of the disk. Their increasing gravity allows them to sweep up smaller objects, further accelerating their growth. This phase also marks the beginning of differentiation, where internal heat, generated by radioactive decay and the energy of impacts, causes heavy elements to sink to the core, while lighter materials rise to form a mantle and crust. During this time, the composition of a protoplanet is heavily influenced by its location within the disk. In the inner regions, closer to the star, high temperatures favor the formation of rocky planets composed of silicates and metals. Further out, beyond the frost line, icy materials become abundant, allowing for the creation of gas and ice giants. This gradient in temperature and material availability creates distinct zones within the disk, each with its own planetary characteristics. As protoplanets grow, their gravitational influence extends outward, creating gaps and spirals in the disk. These features are not merely cosmetic. They indicate regions where material is being actively sculpted and redistributed. Protoplanets also interact with one another, leading to collisions that can merge smaller bodies or disrupt their growth. These interactions, along with the dynamics of the disk, help determine the final arrangement of planets in a system. The final stage of planetary formation involves clearing the debris and establishing stable orbits. This phase, known as the dynamical clearing stage, sees the remaining planetesimals either accreted onto planets, ejected from the system, or ground into smaller particles by collisions. Giant planets play a significant role during this time, as their immense gravity can scatter material across the system, influencing the formation of moons, asteroid belts, and comets. One of the remarkable aspects of the planet-building process is its universality. Observations of protoplanetary disks around other stars reveal similar patterns of growth and evolution. Rings, gaps, and spirals in these disks, captured by instruments like ALMA, suggest that the processes leading from pebbles to planets are consistent across the galaxy. These observations also highlight the diversity of outcomes, from systems with tightly packed super-Earths to those with massive gas giants in distant orbits. The timescales for planetary formation vary, depending on the size and location of the planet. Small, rocky planets may form within tens of millions of years, while gas giants require the rapid accretion of gas before the disk dissipates, often within just a few million years. These differences underscore the delicate balance required for planets to emerge and survive in the turbulent environment of a young star system. Understanding the step-by-step process of planetary formation is not just about explaining how planets come to be. It also provides insights into the potential for life elsewhere in the universe. The delivery of water, organic molecules, and other volatiles to young planets is a direct result of these processes. For example, icy bodies scattered inward by migrating gas giants may have seeded Earth with the ingredients for life. From pebbles drifting in a disk to fully formed planets orbiting their stars, the story of planetary formation is one of transformation and resilience. Each stage, from the microscopic to the monumental, represents a triumph of natural forces working in concert. As we continue to explore this process, both through observations and simulations, we gain not only a deeper understanding of our cosmic origins, but also a glimpse into the incredible diversity of worlds scattered throughout the galaxy. The chemical composition of a protoplanetary disk is the palette from which planets are painted, influencing their size, structure, and potential for habitability. Variations in the abundance of elements and compounds within a disk result in a dazzling diversity of planets, from scorched rocky worlds to frigid gas giants cloaked in thick atmospheres. Understanding the role of chemical composition in planetary diversity is key to deciphering how planetary systems form and evolve. At the heart of planetary diversity lies the star itself. The metallicity of a star, its abundance of elements heavier than hydrogen and helium, directly impacts the composition of its protoplanetary disk. Stars with higher metallicity tend to have disks richer in solids, which fosters the rapid growth of planetesimals and protoplanets. Observations have shown that stars with higher metallicity are more likely to host gas giants, as the increased availability of heavy elements accelerates the formation of massive cores capable of capturing thick gaseous envelopes. The distribution of elements within the disk is not uniform. Temperature gradients create distinct regions where different materials can condense. Closer to the star, intense heat vaporizes volatile compounds like water, methane, and ammonia, leaving behind heavier elements such as silicates and metals. These refractory materials dominate the inner disk, where rocky terrestrial planets form. Further out, cooler temperatures allow volatile compounds to condense into ices, providing the raw materials for gas and ice giants. This division, marked by the frost line or snow line, plays a critical role in determining planetary composition. Within the frost line, planets tend to be smaller and denser, composed primarily of rock and metal. Beyond the frost line, the abundance of ices and gas enables the formation of larger, lower-density planets with thick atmospheres. This gradient explains why our solar system features rocky planets near the sun and gas and ice giants farther out. Chemical composition also determines the atmosphere of a planet, which in turn influences its surface conditions and habitability. Rocky planets with sufficient gravity can retain atmospheres composed of elements and compounds present in the disk. For example, Earth's atmosphere was shaped by volcanic outgassing and the delivery of volatiles by comets and asteroids. In contrast, gas giants like Jupiter and Saturn retain their primordial hydrogen-helium atmospheres, reflecting the dominant composition of the protoplanetary disk. The availability of specific elements, such as carbon, oxygen, nitrogen, and sulfur, plays a significant role in defining planetary characteristics. These elements form the basis of organic chemistry and are crucial for the development of life. The relative abundance of carbon and oxygen, in particular, can influence the types of molecules that form. For instance, disks with higher carbon-to-oxygen ratios may favor the formation of carbon-rich planets with unusual compositions, including surfaces covered in graphite or diamond-like structures. One of the most intriguing aspects of chemical composition is its connection to planetary migration. As planets move through the disk, they interact with regions of varying chemical makeup, potentially altering their own composition. For example, migrating gas giants may capture ices and volatiles from outer regions, enriching their atmospheres with water and other compounds. This process can also scatter planetesimals inward, delivering water and organic molecules to terrestrial planets, as is thought to have happened with Earth. The influence of chemical composition extends beyond individual planets to entire planetary systems. Systems with high metallicity are more likely to produce multiple gas giants, while those with lower metallicity may be dominated by smaller, rocky planets. This correlation helps explain the diversity of systems observed in the galaxy, from tightly packed super-Earth systems to those with widely spaced gas giants. Recent observations of exoplanets have revealed a stunning variety of atmospheric compositions, highlighting the role of chemical diversity in planetary evolution. Using tools like the Hubble Space Telescope and ground-based spectrographs, astronomers have detected water vapor, methane, carbon dioxide, and even exotic compounds like titanium oxide in exoplanetary atmospheres. These findings not only showcase the diversity of planetary environments, but also provide clues about the processes that shaped them. The study of chemical composition also informs our understanding of habitability. The presence of water, a key ingredient for life, depends on the availability of hydrogen and oxygen in the disk. Similarly, the abundance of carbon and nitrogen influences the potential for complex organic chemistry. By analyzing the chemical makeup of protoplanetary disks, scientists can identify systems with the potential to host habitable worlds. One of the most exciting frontiers in this field is the study of carbon-rich planets. These worlds, thought to form in disks with high carbon-to-oxygen ratios, challenge traditional assumptions about planetary composition. Instead of silicate-rich surfaces, carbon planets may feature exotic materials like carbides and hydrocarbons. While their potential for habitability remains uncertain, they represent a fascinating example of how chemical diversity shapes planetary possibilities. Another critical factor is the role of heavy elements, often referred to as metals in astronomical terms, in determining core formation and differentiation. Planets with higher concentrations of iron and nickel are more likely to develop metallic cores, which can generate magnetic fields. These fields, in turn, protect atmospheres from stellar wind and radiation, increasing a planet's potential for habitability. Earth's magnetic field, for instance, is a product of its iron-rich core. Chemical composition also influences the longevity and stability of planetary atmospheres. The balance between greenhouse gases like carbon dioxide and water vapor determines a planet's surface temperature and climate. On Venus, a runaway greenhouse effect has created a hellish environment, while Earth's delicate balance allows for liquid water and life. Understanding these processes helps us identify exoplanets with conditions similar to our own. The role of chemical composition in planetary diversity is not just an academic question. It has profound implications for the search for life. By studying the chemical signatures of exoplanets, astronomers hope to identify worlds with the right mix of elements and compounds to support life. Missions like the James Webb Space Telescope and upcoming ground-based observatories will enable detailed analyses of exoplanetary atmospheres, bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? The diversity of planets, shaped by their chemical compositions, is a testament to the complexity and creativity of the cosmos. Each planet, whether a rocky super-Earth or a gas giant cloaked in methane, carries the signature of the materials that formed it. By unraveling these chemical stories, we not only deepen our understanding of planetary formation, but also expand our vision of what is possible in the universe. Ring systems and moons are among the most captivating features of planetary systems, acting as the celestial companions and adornments of planets. Far from being mere accessories, they play vital roles in the dynamics, evolution, and even habitability of their host planets. From the iconic rings of Saturn to the diverse moons of Jupiter, these features provide a window into the processes that shape planetary systems and their intricate interactions. Ring systems, with their striking beauty, are most famously associated with the gas giants of our solar system. Saturn's rings are the most prominent, consisting of billions of particles ranging in size from micrometers to meters, primarily composed of water ice with traces of rock and organic material. These rings are not solid structures but dynamic systems influenced by gravitational interactions with the planet and its moons. Their formation and persistence remain subjects of scientific intrigue. The origins of planetary rings are varied and complex. In some cases, rings may form from the remnants of moons or other bodies that were destroyed by tidal forces when they ventured too close to their planet. This process, known as Roche limit disruption, occurs when the gravitational forces exerted by the planet overcome the structural integrity of the orbiting body, breaking it apart. Alternatively, rings can form from the debris left behind by collisions between moons, asteroids, or comets. Once formed, rings are shaped and maintained by interactions with the planet's gravitational field and its moons. These moons, often referred to as shepherd moons, exert gravitational forces that confine the particles within narrow ring boundaries, creating gaps and ripples in the ring structure. The gaps in Saturn's rings, such as the Cassini division, are a direct result of these interactions. Ring systems are not exclusive to Saturn. All the gas giants in our solar system, Jupiter, Uranus, and Neptune, have rings, though they are less prominent. Jupiter's rings are faint and composed mainly of dust particles, likely generated by micrometeoroid impacts on its smaller moons. Uranus and Neptune's rings are darker and more enigmatic, suggesting a composition rich in carbon-based material. The diversity of ring systems highlights the varying conditions and histories of their host planets. Beyond the gas giants, some smaller bodies like the dwarf planet Haumea and the centaur Chariklo also exhibit rings. These discoveries suggest that ring formation is not limited to large planets, but can occur in a variety of environments under the right conditions. Understanding these smaller, less well-known ring systems provides valuable insights into the processes that govern planetary and satellite interactions across the cosmos. Moons, or natural satellites, are even more diverse than rings, ranging from tiny, irregularly shaped rocks to large, planet-like bodies. In our solar system, the gas giants are home to the most numerous and varied moons. Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, exemplify this diversity. Each of these moons is a world unto itself, with unique geological and atmospheric characteristics. Io, the most volcanically active body in the solar system, is a testament to the power of tidal heating. The gravitational forces exerted by Jupiter and its other moons create internal friction within Io, generating immense heat and driving its volcanic activity. This process illustrates how moons can be geologically active even when far from the sun's warming influence. Europa, on the other hand, is an icy world with a subsurface ocean beneath its frozen crust. The presence of this ocean, maintained by tidal heating, makes Europa a prime candidate for hosting extraterrestrial life. Similar oceans are thought to exist on other moons, such as Saturn's Enceladus, which has been observed ejecting water vapor and organic compounds through plumes in its icy surface. Ganymede, the largest moon in the solar system, boasts a magnetic field, a rarity for moons, and a complex geological history. Callisto, with its heavily cratered surface, serves as a time capsule of the solar system's early history, preserving evidence of ancient impacts and processes. Saturn's moons are equally fascinating, with Titan standing out as a world with a thick atmosphere and surface lakes of liquid methane and ethane. Titan's atmosphere, rich in organic molecules, mirrors conditions that may have existed on the early Earth, making it a key target for astrobiological research. Enceladus, with its plumes of water vapor and organic materials, further expands the possibilities for life in subsurface oceans. The icy moons of Uranus and Neptune, though less explored, are intriguing in their own right. Miranda, a moon of Uranus, displays an extraordinary mix of geological features, suggesting a history of intense tectonic activity. Triton, Neptune's largest moon, is thought to be a captured Kuiper Belt object, with active geysers and a retrograde orbit that sets it apart from other moons. Moons are not limited to the outer planets. Earth's moon, our closest celestial neighbor, has profoundly influenced our planet's evolution. Its gravitational pull stabilizes Earth's axial tilt, moderating the planet's climate and seasons. The moon's formation, likely the result of a giant impact early in Earth's history, exemplifies the dramatic events that can shape planetary systems. Even Mars has two small moons, Phobos and Deimos, likely captured asteroids. Their irregular shapes and proximity to Mars hint at the diverse origins and fates of natural satellites. Moons and rings are not isolated features. They interact with each other and their host planets in complex ways. These interactions influence orbital stability, tidal heating, and even the long-term evolution of the planet's rotation. For example, tidal forces between Earth and the Moon are gradually slowing Earth's rotation and pushing the Moon farther away. The study of moons and rings extends beyond our solar system. Exoplanetary systems have revealed tantalizing hints of exomoons, moons orbiting planets outside our solar system. While none have been definitively confirmed, the detection of exomoons would open a new frontier in planetary science, providing insights into the formation and evolution of satellite systems in a variety of environments. Moons and rings are more than celestial adornments. They are dynamic participants in the story of planetary systems. From shaping orbital dynamics to influencing the potential for life, these sidekicks play critical roles in the evolution of their hosts. As our exploration of the solar system and beyond continues, these fascinating companions will remain key to unlocking the secrets of the cosmos. The role of chaos in planetary formation and evolution is a testament to the dynamic and often unpredictable forces that shape the cosmos. Gravitational instability, in particular, is a powerful mechanism that governs the early stages of planetary system formation and continues to influence their long-term evolution. From the formation of planetesimals to the migration of giant planets, gravitational chaos is both a creator and a disruptor, sculpting the architecture of planetary systems. Gravitational instability refers to the process by which a region of a protoplanetary disk becomes dense enough for its own gravity to overcome internal pressures and cause it to collapse. This phenomenon is a key driver of planet formation in certain scenarios, particularly in the outer regions of disks where conditions favor rapid collapse. While the more gradual process of core accretion dominates the formation of smaller, rocky planets, gravitational instability offers an alternative pathway for forming massive gas giants and even brown dwarfs. In the early stages of a protoplanetary disk's life, the interplay between gravity, pressure, and rotation creates a delicate balance. Turbulence, temperature gradients, and variations in density can disrupt this equilibrium, leading to localized instabilities. When a region of the disk becomes sufficiently dense, it may collapse under its own gravity, forming a clump of material. These clumps can grow rapidly, bypassing intermediate stages of planet formation and evolving directly into massive objects. The role of gravitational instability is particularly significant in explaining the formation of gas giants through the disk instability model. Unlike the core accretion model, which requires the gradual buildup of a rocky or icy core before accumulating gas, disk instability allows for the rapid formation of gas giants in regions of the disk where cooling is efficient. This process may explain the presence of massive gas giants in young systems where time constraints make core accretion unlikely. Gravitational instability is not limited to the early stages of planet formation. Even after planets form, chaotic gravitational interactions between them can lead to dramatic changes in their orbits and dynamics. These interactions often result in periods of instability that can reshape an entire planetary system. For example, close encounters between planets can eject smaller bodies from the system, send them into highly eccentric orbits, or cause collisions that merge or destroy planets. One striking example of gravitational chaos is the NICE model, which describes the early evolution of our solar system. According to this model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, once existed in a more compact configuration. Gravitational interactions between these planets, combined with the influence of a surrounding disk of planetesimals, led to a period of instability. This chaotic phase caused the planets to migrate to their current positions, scattering smaller bodies throughout the solar system and triggering the late heavy bombardment. Gravitational instability also plays a role in planetary migration. As planets form and interact with the disk, they create waves and gaps that influence their motion. These interactions can destabilize their orbits, causing them to move inward or outward. The chaotic nature of these migrations explains why some exoplanetary systems feature hot Jupiters or tightly packed super-Earths, while others have widely spaced planets or no large planets at all. In addition to shaping the orbits of planets, gravitational instability influences the formation and evolution of moons and rings. The tidal interactions between a planet and its moons, as well as the gravitational interactions between moons themselves, create complex dynamical systems. These interactions can lead to the capture of moons, the formation of resonances, and even the destruction of satellites that stray too close to their planet's Roche limit. Gravitational chaos is also evident in the formation of debris disks and asteroid belts. These features often arise from the remnants of planet formation, sculpted by the gravitational influence of nearby planets. For example, the gaps and resonances in the asteroid belt between Mars and Jupiter are shaped by Jupiter's gravitational field, which prevents material from coalescing into a planet. Observations of exoplanetary systems reveal the prevalence of gravitational instability and its impact on planetary diversity. Many systems feature eccentric orbits, resonant configurations, and evidence of past dynamical upheavals. These characteristics suggest that chaotic gravitational interactions are a universal aspect of planetary system evolution. Simulations of planetary systems provide insights into the chaotic processes that govern their formation and evolution. These models reveal how small differences in initial conditions can lead to vastly different outcomes, emphasizing the sensitivity of planetary systems to gravitational interactions. For instance, a slight change in the mass or position of a planet can alter the stability of the entire system, leading to outcomes ranging from stable orbits to complete disintegration. While gravitational chaos often appears destructive, it is also a creative force. The scattering of planetesimals and debris can deliver water and other volatiles to rocky planets, contributing to the development of habitable environments. Similarly, the capture of moons through chaotic interactions adds complexity and diversity to planetary systems. Gravitational instability is not merely a relic of the past. It continues to influence mature planetary systems. Long-term gravitational interactions between planets can lead to changes in their orbits over billions of years. These processes are particularly relevant in multi-planet systems, where resonance and secular perturbations can drive slow but significant evolution. The study of gravitational instability highlights the delicate balance between order and chaos in the universe. While the forces at play are inherently unpredictable, their outcomes are evident in the rich diversity of planetary systems we observe. From the rapid formation of gas giants to the slow evolution of orbital resonances, gravitational chaos shapes the fates of worlds, reminding us that the cosmos is both dynamic and ever-changing. The transition from dust to life is one of the most profound and mysterious processes in the universe. Planets, born from the debris of stars, evolve into worlds capable of hosting life under the right conditions. This transformation involves a delicate interplay of physical, chemical, and biological processes, each building on the last to create environments where life can emerge, thrive, and evolve. The foundation of life begins with the materials available in the protoplanetary disk. These disks, composed of gas and dust, contain the essential elements for life: hydrogen, oxygen, carbon, nitrogen, sulfur, and phosphorus. These elements, forged in the cores of stars and distributed throughout the galaxy by supernovae and stellar winds, combine to form simple molecules like water, H2O, methane, CH4, ammonia, NH3, and carbon dioxide, CO2. These molecules are the raw ingredients for more complex organic compounds, such as amino acids and nucleotides, which are essential for life as we know it. The delivery of these compounds to planets is a critical step in fostering conditions for life. In the early solar system, comets, asteroids, and planetesimals played a key role in delivering water and organic molecules to Earth and other planets. This process, known as late-stage accretion, enriched the inner planets with the volatiles necessary for creating habitable environments. Impact events, while often catastrophic, also provided energy for chemical reactions and deposited materials that could kickstart prebiotic chemistry. Once a planet forms, its potential to support life depends on a combination of factors, including its size, composition, distance from its star, and geological activity. The planet's location within the habitable zone, where temperatures allow for liquid water to exist on the surface, is particularly crucial. This zone varies depending on the star size and luminosity, but it provides a basic framework for identifying planets that might harbor life. Geological activity is another key factor in fostering life. Active geology contributes to the recycling of nutrients and the regulation of atmospheric composition, both of which are essential for sustaining a stable environment. Plate tectonics, for example, plays a significant role in Earth's carbon cycle, balancing the levels of carbon dioxide in the atmosphere and preventing runaway greenhouse or icehouse conditions. Volcanic activity can also release gases that contribute to the formation of atmospheres and provide energy sources for microbial life. Magnetic fields generated by a planet's core protect its surface from harmful solar and cosmic radiation. On Earth, the geomagnetic field shields the atmosphere from being stripped away by the solar wind, preserving the conditions necessary for liquid water and life. Without such a field, planets like Mars and Venus have experienced dramatic atmospheric losses, rendering their surfaces inhospitable. Water, often considered the universal solvent, is fundamental to life as we know it. Its unique properties allow it to dissolve and transport nutrients, facilitate chemical reactions, and stabilize temperatures. The presence of water on a planet's surface or in its subsurface layers greatly enhances its potential to support life. Liquid water reservoirs, whether in oceans, lakes, or underground aquifers, provide stable environments where life can take root and evolve. Atmospheres are another critical component of habitable worlds. A planet's atmosphere regulates its temperature, protects it from radiation, and facilitates the cycling of gases like carbon dioxide and oxygen. The composition of an atmosphere can also signal the presence of biological activity. For instance, Earth's atmosphere contains high levels of oxygen and methane, maintained in a state of disequilibrium by life processes. Detecting similar atmospheric signatures on exoplanets would be a compelling indication of potential life. The emergence of life requires not only the right environmental conditions, but also a spark of complexity. On Earth, life is thought to have originated in environments such as hydrothermal vents, shallow tidal pools, or even icy environments where chemical reactions could proceed in relative stability. These settings provided the necessary energy sources and chemical gradients for the formation of self-replicating molecules, a key step in the origin of life. Once life emerges, its evolution is shaped by the planet's environment and geological history. The interaction between life and its surroundings can create feedback loops that drive further changes. For example, early microbial life on Earth played a role in oxygenating the atmosphere during the Great Oxidation Event, transforming the planet and paving the way for more complex organisms. The search for life beyond Earth focuses on identifying planets and moons with the potential to replicate these processes. Mars, with its history of water and potential subsurface reservoirs, remains a prime target. Similarly, the icy moons Europa, Enceladus, and Titan are of great interest due to their subsurface oceans and chemical diversity. These environments could host microbial life, even in the absence of sunlight, through chemosynthesis, a process by which organisms derive energy from chemical reactions rather than photosynthesis. Exoplanet discoveries have expanded the scope of habitable environments, revealing that planets with thick atmospheres, subsurface oceans, or even exotic chemistries could support life in forms vastly different from those on Earth. Super-Earths, with their larger sizes and potentially thicker atmospheres, might offer stable environments conducive to life, while planets orbiting red dwarfs could have extended habitable zones due to the longevity of their host stars. Advances in technology are bringing us closer to detecting signs of life on distant worlds. The James Webb Space Telescope, along with upcoming missions like the Extremely Large Telescope, (ELT), and the Nancy Grace Roman Space Telescope, aims to study the atmospheres of exoplanets in unprecedented detail. These instruments will search for biosignatures, chemical markers such as oxygen, methane, and ozone, that could indicate the presence of life. While the conditions for life, as we know it, are relatively specific, the possibility of alternative biochemistries broadens the scope of habitability. Life based on solvents other than water, such as methane or ammonia, could thrive in environments vastly different from those on Earth. Titan, with its hydrocarbon lakes and methane-rich atmosphere, exemplifies the potential for exotic forms of life. The transformation of planets from dust to life is a story of cosmic ingenuity and resilience. It underscores the interconnectedness of physical and chemical processes that create habitable worlds. As we continue to explore our solar system and beyond, we are not only seeking other examples of this incredible transformation, but also deepening our understanding of the conditions that made life possible on Earth. The solar system serves as a blueprint for understanding planetary formation, evolution, and the dynamics of celestial systems. By studying our cosmic neighborhood, we uncover the intricate processes that shape planets, moons, asteroids, and comets, gaining insights that apply to the countless systems scattered throughout the galaxy. Each component of the solar system offers a clue to the forces that govern not only its history, but also the diversity of exoplanetary systems. At the center of this blueprint lies the Sun, the solar system's engine. Its gravitational pull binds the system together, while its light and heat influence the behavior of planets and other bodies. The Sun's composition, primarily hydrogen and helium with trace amounts of heavier elements, reflects its status as a second-generation star, enriched by the remnants of earlier stellar generations. This chemical inheritance provided the raw materials for the formation of the planets and their diverse compositions. The solar system's architecture, with small rocky planets close to the Sun and gas giants farther out, reflects the influence of temperature gradients in the protoplanetary disk. The inner solar system, where high temperatures vaporized volatile compounds, became the realm of silicates and metals, forming Mercury, Venus, Earth, and Mars. Beyond the frost line, cooler conditions allowed ices and gases to condense, enabling the formation of Jupiter, Saturn, Uranus, and Neptune. Jupiter, the solar system's largest planet, played a pivotal role in shaping the system's structure. Its immense gravity acted as a cosmic gatekeeper, preventing the formation of a planet in the asteroid belt and influencing the orbits of comets and asteroids. Jupiter's migration, as described by the Grand Tack hypothesis, likely scattered planetesimals throughout the system, delivering water and organic materials to the inner planets and contributing to Earth's habitability. Saturn, with its stunning ring system, highlights the dynamic interactions between planets and their satellites. Its moons, from the methane-rich Titan to the icy, ocean-bearing Enceladus, illustrate the diversity of conditions that can arise within a single planetary system. The rings themselves, composed of ice and rock, are a testament to the processes of tidal disruption and gravitational sculpting. The ice giants, Uranus and Neptune, add another layer to the solar system's blueprint. Their compositions, dominated by water, ammonia, and methane, differ significantly from those of Jupiter and Saturn. Their tilted and eccentric orbits suggest that interactions with each other or with a now-lost sibling planet may have influenced their current positions, offering a glimpse into the chaotic dynamics of planetary systems. The inner planets, while smaller in scale, reveal the complexities of planetary evolution. Mercury, with its iron-rich core and thin crust, suggests a violent history of impacts and material loss. Venus, with its thick atmosphere and runaway greenhouse effect, demonstrates the delicate balance required to maintain habitable conditions. Mars, with its ancient riverbeds and polar ice caps, offers tantalizing evidence of a wetter, potentially habitable past. Earth stands out as a unique example of a life-bearing planet, but its characteristics are deeply connected to the solar system's history. The Moon, formed from a giant impact, stabilizes Earth's axial tilt and influences its climate. The planet's position in the habitable zone, combined with its magnetic field, plate tectonics, and atmosphere, creates a rare set of conditions that support life. The asteroid belt, Kuiper belt, and Oort cloud provide additional pieces of the solar system's puzzle. These regions, populated by remnants of the planet-forming process, serve as archives of the early solar system. Asteroids, with their varied compositions, reveal the chemical gradients in the protoplanetary disk. Comets, with their icy nuclei, carry primordial materials that may have delivered water and organic compounds to the inner planets. The study of the solar system extends beyond its current state to its formation and evolution. Models of the early solar system suggest a period of intense dynamism, with migrating planets, frequent collisions, and shifting orbits. The NICE model, for example, explains how the giant planet's interactions with a disk of planetesimals could have scattered material throughout the system, creating the Kuiper Belt and triggering the late heavy bombardment. The solar system also provides a framework for understanding exoplanetary systems. Observations of other stars reveal systems with hot Jupiters, super-Earths, and tightly packed planetary configurations, challenging the traditional view of planet formation. By comparing these systems to our own, scientists identify the factors that contribute to their diversity and gain a deeper understanding of the processes that create habitable worlds. One of the key lessons from the solar system is the importance of small bodies in shaping planetary systems. Asteroids and comets, often overlooked as mere debris, play critical roles in delivering essential materials, influencing planetary climates, and recording the history of the disk from which planets formed. Missions like OSIRIS-Rx, Hayabusa 2, and the Rosetta spacecraft have highlighted the wealth of information these bodies provide. The solar system's moons offer another layer of complexity. From the volcanic activity of Io to the icy oceans of Europa and Enceladus, these natural satellites demonstrate the potential for habitability beyond planets. Their diverse environments challenge traditional notions of where life might exist and expand the search for extraterrestrial organisms. The solar system is not just a collection of planets and debris. It is a dynamic system governed by gravitational interactions, chemical processes, and evolutionary forces. Each component, from the smallest asteroid to the largest gas giant, contributes to the overall structure and behavior of the system. By studying it, we gain not only a deeper understanding of our own origins, but also a roadmap for exploring the countless other systems in the universe. As we continue to explore the solar system through missions like Perseverance, Europa Clipper, and the James Webb Space Telescope, we refine our blueprint of planetary systems. These discoveries not only enhance our knowledge of the cosmos, but also bring us closer to answering the fundamental question: what makes a world habitable? And are we alone in the universe? The field of planetary formation, while vastly advanced, is still rife with unanswered questions. As we continue to probe the cosmos with ever more sophisticated tools and techniques, we find ourselves grappling with mysteries that challenge our understanding of how worlds are born and evolve. These questions not only drive the future of planetary science, but also shape our quest to understand the universe and our place within it. One of the most pressing questions is, what determines the diversity of planetary systems? Observations of exoplanets reveal an astonishing variety of worlds: hot Jupiters, super-Earths, mini-Neptunes, and planets in eccentric orbits that defy traditional models based on our solar system. Why do some systems host tightly packed planets close to their star, while others feature widely spaced or even single planets? The role of initial conditions, such as the mass and metallicity of the protoplanetary disk, as well as the influence of stellar activity, remains a subject of active research. The origin of super-Earths and mini-Neptunes is another significant puzzle. These planet types are common in other systems but absent in our own. Are they scaled-up rocky planets? Or do they form more like gas giants? Do they represent a distinct class of planets? Or are they evolutionary stages of other types? Understanding how these intermediate planets form and evolve could reveal why our solar system lacks them and what that absence means for habitability. How do planetary atmospheres evolve? The development and retention of a planet's atmosphere are crucial for determining its surface conditions and potential habitability. Processes like atmospheric escape, volcanic outgassing, and impacts can dramatically alter a planet's atmosphere over time. For example, Venus, Earth, and Mars started with similar building blocks, but evolved vastly different atmospheres. Why did Earth develop a life-supporting atmosphere, while Venus became a greenhouse inferno and Mars a frozen desert? The role of magnetic fields in planetary evolution is also poorly understood. Magnetic fields protect planets from stellar winds and cosmic radiation, preserving their atmospheres and enabling conditions for life. Yet, not all planets generate such fields. What factors determine whether a planet can sustain a magnetic field, and how does the presence or absence of one affect its evolution? Another frontier lies in understanding the formation of moons and ring systems. While the giant planets' moons and rings have been studied extensively, the processes that create and maintain these systems remain enigmatic. Why do some planets, like Mars, have small, irregular moons, while others, like Jupiter and Saturn, host complex systems of large moons and intricate rings? The capture of moons, tidal interactions, and the destruction of existing satellites are all factors, but the relative importance of each is still debated. The study of planetary migration poses additional challenges. Migration plays a pivotal role in shaping planetary systems, yet its mechanisms and outcomes are not fully understood. For example, why do some migrating gas giants stop close to their stars, becoming hot Jupiters, while others settle in distant orbits? What role does migration play in the formation and destruction of smaller terrestrial planets? The Grand Tack hypothesis, which suggests Jupiter's migration shaped the inner solar system, provides a compelling narrative for our own history. But is this pattern common or unique? How common are habitable worlds? While the discovery of Earth-sized planets and habitable zones is a milestone, habitability depends on more than size and distance from a star. Factors such as atmospheric composition, magnetic fields, geological activity, and stellar variability all influence whether a planet can support life. Are there Earth-like planets with stable climates? Or do most rocky planets face the runaway greenhouse or atmospheric collapse scenarios of Venus and Mars? The possibility of alternative biochemistries expands the scope of habitability, but also complicates the search for life. While Earth-based life depends on water and carbon-based molecules, could life arise in environments with different solvents, such as liquid methane on Titan, or alternative chemistries, such as silicon-based compounds? How do we detect life that may not fit the template we know? The formation and evolution of gas giants also remain areas of active investigation. While the core accretion model is well supported, the rapid timescales required for gas giant formation in certain systems suggest that disk instability may play a larger role than previously thought. How do these massive planets form in systems with sparse disks or short-lived gas reservoirs? Do the same processes operate universally, or are they highly dependent on specific conditions? The study of planetary system architecture raises questions about the role of dynamical interactions. How do multi-planet systems maintain stability over billions of years? What triggers the chaotic rearrangement seen in some systems, where planets are ejected or flung into eccentric orbits? Understanding these interactions can illuminate why our solar system appears unusually stable compared to many exoplanetary systems. Finally, the question of life's emergence looms large. While the solar system provides clues, such as the presence of water and organic molecules on Earth, Europa, and Enceladus, we still do not know the specific conditions or processes that lead to life. Did life on Earth arise from local processes, or was it seeded by materials from space? Could similar processes occur elsewhere, or is life an exceedingly rare phenomenon? To address these questions, future missions and technologies are essential. Space telescopes like the James Webb Space Telescope and the upcoming Roman Space Telescope will allow detailed studies of exoplanetary atmospheres, while ground-based observatories like the Extremely Large Telescope, ELT, will provide unprecedented precision in detecting and characterizing distant worlds. Missions to icy moons, such as Europa Clipper and Dragonfly, to Titan, will explore the potential for life in subsurface oceans and exotic environments. Laboratory experiments and simulations also play a vital role, recreating the conditions of protoplanetary disks, planetary surfaces, and atmospheres to test hypotheses about planet formation and habitability. Advances in computational power enable more detailed models of planetary systems, revealing how small changes in initial conditions can lead to vastly different outcomes. The unanswered questions in planetary formation are not just scientific curiosities. They are keys to understanding the nature of the universe and humanity's place within it. As we push the boundaries of exploration and discovery, we may find that the answers lie not only in distant star systems, but also in the rich history written across our own solar system. The study of planetary formation continues to evolve, driven by emerging theories and groundbreaking research that challenge long-held assumptions and open new avenues of exploration. With each discovery, our understanding of how planets form, migrate, and interact becomes more nuanced, revealing the complexity and diversity of planetary systems. This chapter delves into the latest theories and research shaping the field, offering insights into the next frontier of planetary science. One of the most transformative developments is the growing recognition of the role of disk dynamics in shaping planetary systems. Traditional models treated protoplanetary disks as relatively uniform and static, but new observations reveal a far more dynamic picture. Disks are now understood to be turbulent environments, with pressure gradients, magnetic fields, and chemical variations creating localized regions of activity. These features can form pressure bumps, where dust and gas concentrate, accelerating the growth of planetesimals and potentially bypassing the meter-size barrier. Recent simulations suggest that these pressure bumps may also explain the formation of super-Earths and mini-Neptunes, as well as the rapid assembly of gas giants. By trapping solid material in specific regions, these features create fertile zones for planetary growth. Observations from the Atacama Large Millimeter/Submillimeter Array, ALMA, have confirmed the presence of such structures in protoplanetary disks, including rings, gaps, and spirals that hint at the locations of forming planets. Another emerging area of research focuses on the chemical composition of protoplanetary disks. Advanced spectroscopy techniques are revealing intricate details about the distribution of elements and molecules within disks. For example, the discovery of water-rich regions and complex organic molecules in young disks suggests that the building blocks of life are common throughout the galaxy. This research underscores the importance of understanding how these materials are incorporated into forming planets, particularly those in the habitable zone. Theories about planetary migration are also undergoing revision. While the inward migration of hot Jupiters is well established, new models suggest that migration is a far more complex and varied process. For instance, some planets may migrate outward due to interactions with gas and dust, while others may oscillate between inward and outward paths before settling into stable orbits. The discovery of planets in highly eccentric orbits challenges traditional models, suggesting that dynamical interactions, such as planet-planet scattering, play a significant role in shaping orbital configurations. The role of disk instability in planet formation is receiving renewed attention, particularly in the context of massive gas giants and brown dwarfs. While core accretion remains the dominant model for most planets, disk instability offers a faster mechanism for forming massive bodies in regions of the disk where cooling is efficient. Recent studies suggest that both mechanisms may operate simultaneously in different parts of a disk, contributing to the diversity of planetary systems. The concept of planetary pebble accretion is gaining traction as a key mechanism in the early stages of planet formation. In this model, growing protoplanets accrete small, millimeter-sized particles, pebbles, from the surrounding disk, rather than relying solely on collisions with larger planetesimals. Pebble accretion is highly efficient, allowing planets to grow rapidly and potentially explaining the formation of gas giants within the limited lifetime of protoplanetary disks. Exoplanet discoveries are continuously refining our understanding of planetary system architecture. The prevalence of compact, multi-planet systems with orbital resonances, such as those around TRAPPIST-1 and Kepler-223, suggests that migration and dynamical interactions are central to the evolution of these systems. These findings challenge the traditional view that planetary systems should resemble our own, highlighting the role of initial conditions and disk properties in shaping outcomes. The study of exomoons represents an exciting new frontier in planetary science. While moons play critical roles in our solar system, their counterparts around exoplanets remain elusive. The first potential detection of an exomoon, orbiting the gas giant Kepler-1625b, has sparked intense interest in understanding how moons form and evolve in different environments. Exomoons could also provide additional habitats for life, particularly in cases where tidal heating generates subsurface oceans. The exploration of icy worlds and subsurface oceans is reshaping our understanding of habitability. Moons like Europa, Enceladus, and Titan demonstrate that liquid water and complex chemistry can exist far from a star's habitable zone. Research into these environments suggests that tidal heating and radiogenic decay can sustain liquid water for billions of years, providing stable conditions for life. Missions such as Europa Clipper and Dragonfly are poised to investigate these possibilities further. Theoretical advancements are being complemented by revolutionary observational tools. The James Webb Space Telescope, JWST, launched to study the early universe, has already begun analyzing the atmospheres of exoplanets with unprecedented precision. By detecting key molecules like water vapor, methane, and carbon dioxide, JWST offers the potential to identify biosignatures or other markers of habitability on distant worlds. Ground-based observatories are also pushing the boundaries of planetary science. The Extremely Large Telescope, ELT, set to begin operations in the coming years, will allow direct imaging of exoplanets and their disks. This capability will enable detailed studies of planetary formation in real time, providing a deeper understanding of the processes driving diversity and complexity. In the lab, researchers are recreating the conditions of protoplanetary disks, planetary interiors, and atmospheres to test hypotheses and refine models. Experiments on high-pressure chemistry, for instance, are shedding light on the behavior of materials deep within gas giants and super-Earths. These studies help bridge the gap between theoretical predictions and observational data. The integration of machine learning and artificial intelligence into planetary science is accelerating discoveries. AI algorithms are being used to analyze vast datasets from telescopes, identifying patterns and anomalies that might otherwise go unnoticed. These tools are particularly effective in the search for exoplanets and the characterization of their properties, allowing scientists to probe deeper into the underlying physics and chemistry of planetary systems. As these theories and technologies converge, they bring us closer to addressing fundamental questions about the universe. How common are habitable worlds? What conditions lead to the emergence of life? And are there other planetary systems with histories and dynamics as rich as our own? The emerging theories and groundbreaking research in planetary science are not only reshaping our understanding of the cosmos, but also inspiring new questions. As we look to the future, the next generation of scientists, telescopes, and space missions will undoubtedly uncover even more profound insights into the nature of planets and the intricate processes that bring them to life. The next generation of telescopes and space missions is poised to revolutionize our understanding of planetary formation, evolution, and the conditions for habitability. These cutting-edge instruments will allow scientists to address fundamental questions about the universe, from the origins of planetary systems to the search for life on distant worlds. As the capabilities of observational technology expand, so too does our potential to uncover the secrets of the cosmos. At the forefront of this revolution is the James Webb Space Telescope, JWST. Launched to peer into the earliest epochs of the universe, JWST is also transforming planetary science. Its ability to observe in the infrared spectrum enables detailed studies of exoplanetary atmospheres, revealing the composition of gases like water vapor, methane, and carbon dioxide. By analyzing the light that passes through an exoplanet's atmosphere during a transit, JWST can detect potential biosignatures or chemical imbalances that might indicate biological activity. The telescope's precision and sensitivity make it a key tool for studying rocky planets in the habitable zones of their stars. JWST's potential extends beyond exoplanets to the study of protoplanetary disks. Its observations provide high-resolution images of the regions where planets are forming, capturing the structure of disks, including rings, gaps, and spirals that hint at the presence of nascent planets. These data are crucial for refining models of planetary formation and understanding the role of disk dynamics in shaping planetary systems. Ground-based observatories are also entering a new era, with instruments like the Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, set to begin operations in the coming years. These telescopes, with their immense light-gathering power and adaptive optics, will provide unparalleled views of exoplanets and their host stars. Direct imaging capabilities will allow scientists to study the surfaces and atmospheres of planets, even those located in other star systems. The ELT, for example, will target Earth-like planets in nearby systems, seeking signs of water, oxygen, and other markers of habitability. The Roman Space Telescope, named after Nancy Grace Roman, NASA's first chief astronomer, is another groundbreaking mission on the horizon. Equipped with a wide-field infrared survey instrument, Roman will identify thousands of exoplanets using the microlensing technique, which detects planets by observing how their gravity bends light from a background star. Roman surveys will provide statistical data on the diversity of planetary systems, including the prevalence of Earth-sized planets and the frequency of planets in habitable zones. The study of moons and icy worlds within our solar system is set to advance dramatically with missions like Europa Clipper and Dragonfly. Europa Clipper will investigate Jupiter's moon Europa, a world with a subsurface ocean beneath its icy crust. By analyzing the moon's surface and detecting potential water plumes, Europa Clipper aims to determine whether conditions below the ice could support life. Dragonfly, a drone-like mission to Saturn's moon Titan, will explore its thick atmosphere and methane-rich lakes, searching for prebiotic chemistry and signs of biological processes. Closer to home, Mars exploration continues to play a central role in planetary science. The Perseverance rover, equipped with advanced instruments for analyzing rock samples, is paving the way for the first Mars sample return mission. By bringing Martian materials back to Earth, scientists will have the opportunity to study the planet's geology and search for evidence of past life with a full suite of terrestrial laboratory tools. The Ariel space mission, led by the European Space Agency, ESA, will focus specifically on studying the atmospheres of exoplanets. Ariel's goal is to observe a wide variety of planets, from hot Jupiters to super-Earths, across different star types. By analyzing atmospheric compositions, Ariel will shed light on the processes that govern planetary diversity and evolution, offering insights into how planets form and develop over time. The exploration of asteroids and comets is another exciting frontier. Missions like OSIRIS-Rx, which returned samples from the asteroid Bennu, and Japan's Hayabusa 2, which collected material from Ryugu, have provided invaluable data on the composition of these primitive bodies. These missions help scientists understand the building blocks of planets and the delivery of water and organic materials to Earth. Future missions, such as NASA's Psyche, will study a metallic asteroid, offering clues about planetary core formation. The detection of exomoons remains an elusive but promising goal. Instruments like JWST and YELT are expected to help identify these satellites by detecting their gravitational effects or the light they block during transits. Exomoons could play a critical role in understanding the dynamics of planetary systems and may even offer additional habitats for life, particularly if they host subsurface oceans heated by tidal forces. The next decade will also see the rise of interstellar exploration, with missions designed to study objects that originate outside our solar system, such as Oumuamua and Borisov. These interstellar visitors offer unique opportunities to study materials from other star systems, providing direct insights into the diversity of planetary formation processes across the galaxy. The integration of artificial intelligence, AI, and machine learning into observational astronomy is accelerating the pace of discovery. AI algorithms can sift through vast datasets from telescopes, identifying patterns, anomalies, and new exoplanets that would be difficult or impossible to detect manually. These tools are not only enhancing our ability to analyze data, but also helping to optimize mission planning and telescope operations. The role of telescopes and missions is not limited to observation. They're essential for testing and refining theories. By comparing observational data with models of planetary formation and evolution, scientists can identify gaps in understanding and develop new hypotheses. For example, the unexpected prevalence of planets in tightly packed orbits, revealed by Kepler and TESS, has prompted revisions to theories of planetary migration and disk dynamics. As these new tools and missions come online, they bring us closer to answering some of the most profound questions in science. How do planets form and evolve? What factors determine habitability? And is there life beyond Earth? The discoveries they enable will not only expand our knowledge of the cosmos, but also deepen our understanding of the processes that gave rise to our own world. The origins of planets are written in the chaotic and intricate interactions of matter and energy within protoplanetary disks. Advanced models and simulations, powered by ever-increasing computational capabilities, are revolutionizing our ability to decode these processes. These tools allow scientists to recreate the conditions of young star systems, test hypotheses about planetary formation and evolution, and uncover phenomena that are otherwise hidden from observation. At the heart of modern planetary science is the ability to simulate the formation of planets, from the earliest stages of dust coagulation to the assembly of fully formed worlds. These simulations incorporate the complex interplay of gravity, hydrodynamics, thermodynamics, and chemical reactions to model how protoplanetary disks evolve and give rise to diverse planetary systems. One of the major advancements in this field is the development of multi-scale models that bridge the gap between small-scale processes, like the collisions of dust grains, and large-scale phenomena, like the migration of gas giants. These models allow scientists to trace the evolution of a planet-forming disk in unprecedented detail, revealing how localized events can have far-reaching effects on the structure and composition of the system. For example, simulations of dust coagulation and planetesimal formation have shed light on how microscopic particles overcome barriers like fragmentation and radial drift to grow into kilometer-sized bodies. These studies highlight the importance of turbulence and pressure traps in concentrating dust, creating the conditions for rapid accretion. Streaming instabilities, where dust and gas interact to form dense filaments that collapse under gravity, have emerged as a key mechanism for bypassing the meter-sized barrier in planetesimal growth. Simulations also provide critical insights into the core accretion model, the dominant theory for the formation of gas giants. These models track how rocky or icy cores, once they reach a critical mass, rapidly accrete gas from the surrounding disk to form massive planets. By testing different initial conditions, such as disk density, metallicity, and temperature, scientists can explore why some systems produce Jupiter-like giants while others form mini-Neptunes or super-Earths. The study of disk instability has also benefited from advanced modeling. Simulations show how gravitational instabilities in massive, cool disks can create dense clumps of gas that collapse to form planets directly. This mechanism may explain the rapid formation of gas giants in certain systems, particularly those where the lifetime of the protoplanetary disk is too short for core accretion to operate effectively. Another key area of research involves planetary migration. Simulations reveal how interactions between forming planets and their disks create waves and torques that can move planets inward or outward. These studies have illuminated the processes that lead to phenomena like hot Jupiters and compact multiplanet systems. They also show how migration can shape the distribution of material in a system, influencing the formation of terrestrial planets and delivering water and organics to their surfaces. Dynamical simulations of mature planetary systems provide insights into the long-term stability of orbits and the role of gravitational interactions. For example, the NICE model, which simulates the early evolution of the solar system, demonstrates how interactions between Jupiter, Saturn, Uranus, and Neptune triggered a period of instability that scattered planetesimals and reshaped the system's architecture. Such studies highlight the importance of chaos in planetary evolution and explain features like the Kuiper Belt and the Late Heavy Bombardment. One of the most exciting applications of simulations is the study of exoplanetary systems. By recreating the conditions observed in systems like TRAPPIST-1 or HR 8799, scientists can explore how these systems formed and why they differ from our own. These models help answer questions about the prevalence of tightly packed planets, the role of resonances, and the diversity of planetary compositions. Simulations also play a crucial role in understanding atmospheric evolution. Models of atmospheric escape, driven by stellar radiation and impacts, reveal how planets lose or retain their gaseous envelopes over time. These studies are particularly important for understanding super-Earths and mini-Neptunes, which exist in a transitional size range where atmospheric processes are highly sensitive to initial conditions. The exploration of habitable worlds is another frontier for simulations. Climate models, similar to those used for Earth, are being applied to exoplanets to predict their surface temperatures, atmospheric dynamics, and potential for liquid water. These models incorporate factors like the greenhouse effect, stellar variability, and the planet's rotation rate to assess habitability. For example, simulations of tidally locked planets, which always show the same face to their star, reveal how atmospheric circulation might redistribute heat, creating temperate regions even on planets with extreme temperature gradients. Simulations are also critical for studying moons and ring systems. Models of tidal interactions between planets and their satellites reveal how moons evolve over time, potentially becoming stable orbits or spiraling inward to form rings. These studies help explain the diversity of moon systems in the solar system and predict the conditions under which exomoons might form and survive. The integration of chemistry into planetary simulations has opened new doors for understanding the diversity of planetary compositions. By modeling how elements and molecules condense, migrate, and react in a disk, scientists can predict the compositions of forming planets. These models explain trends like the abundance of carbon-rich exoplanets or the depletion of volatiles in the inner regions of disks. Advanced models also incorporate stellar activity, such as flares and winds, which can strip atmospheres or heat the surfaces of planets. These interactions are particularly important for planets orbiting red dwarfs, where intense stellar activity can dramatically affect habitability. The development of machine learning and artificial intelligence, AI, is enhancing the power of simulations. AI algorithms can optimize models, identify patterns in large data sets, and predict outcomes based on incomplete information. These tools are not only accelerating the pace of discovery, but also uncovering relationships and trends that might otherwise go unnoticed. Simulations are invaluable for interpreting observational data. For instance, when telescopes detect a gap in a protoplanetary disk or an eccentric orbit in an exoplanetary system, simulations can provide plausible explanations and identify the underlying processes. This synergy between observations and modeling is key to advancing our understanding of planetary systems. As computational power continues to grow, the resolution and complexity of simulations will improve, enabling scientists to explore new frontiers in planetary science. Whether modeling the chaotic formation of moons, the long-term stability of habitable climates, or the intricate dynamics of multi-planet systems, these tools are essential for unveiling the origins of planets and the forces that shape their fates. The story of planetary formation is one of profound interconnectedness, weaving together the forces of physics, chemistry, and time into a cosmic tapestry that stretches across the universe. From the smallest grains of dust in protoplanetary disks to the sprawling systems of planets and moons, every step in this process is linked by a series of interactions that shape the evolution of celestial bodies. By understanding these connections, we begin to see planetary formation not as a series of isolated events, but as a holistic process that transcends individual systems. At the heart of this interconnectedness lies the cycle of star formation and death. The materials that form planets are forged in the cores of stars and released into space through stellar winds and supernova explosions. These enriched elements seed the interstellar medium, creating the molecular clouds from which new stars and their planetary systems arise. In this way, every planet is a product of cosmic recycling, carrying the signatures of the stars that came before it. Protoplanetary disks, the birthplaces of planets, exemplify the intricate balance of forces at work. These disks are dynamic systems where gravity, angular momentum, and thermodynamics interact to distribute matter and energy. Within the disk, temperature gradients dictate where different materials condense, creating zones that favor the formation of specific types of planets. Rocky worlds form close to the star, where only metals and silicates can survive the heat, while gas and ice giants dominate the cooler, outer regions. As planets form, they interact with the disk, shaping its structure and dynamics. The gravitational influence of growing protoplanets creates gaps, spirals, and waves that affect the distribution of gas and dust. These interactions, in turn, influence the migration of planets, altering their orbits and determining their final configurations. The interplay between planets and their disks highlights the interconnected nature of planetary formation, where each component affects the others in a feedback loop. The relationships between planets themselves further demonstrate this interconnectedness. In multi-planet systems, gravitational interactions can lead to resonances, where planets exert regular, periodic influences on each other's orbits. These resonances can stabilize systems, as seen in the Galilean moons of Jupiter, or destabilize them, resulting in orbital rearrangements, collisions, or ejections. The architecture of a planetary system is thus a product of both its initial conditions and the ongoing gravitational dance of its members. The interconnectedness of planetary formation extends to smaller bodies, such as moons, asteroids, and comets. Moons often form as byproducts of planetary formation, either coalescing from debris disks around planets, being captured from elsewhere, or emerging from massive impacts. These moons, in turn, influence their host planets, stabilizing their axial tilts, driving tidal heating, and contributing to the dynamics of ring systems. Similarly, asteroids and comets play critical roles in delivering water and organic materials to terrestrial planets, bridging the gap between planetary formation and the emergence of life. The chemical composition of planets and their atmospheres further illustrates this cosmic interconnection. The materials available in a protoplanetary disk are shaped by the star's metallicity and the disk's temperature profile. These materials influence not only the bulk composition of planets, but also the evolution of their atmospheres. Volcanic outgassing, impacts, and atmospheric escape are all processes that link a planet's interior to its surface and surroundings, creating a dynamic system where changes in one component affect the others. The emergence of life adds another layer to this web of connections. Life depends on the delivery of essential elements and compounds, such as water, carbon, and nitrogen, which are products of both stellar processes and planetary interactions. Once life arises, it begins to influence its environment, as seen on Earth during the Great Oxidation Event, when microbial activity transformed the atmosphere. This feedback between life and planet creates a self-sustaining system that can persist for billions of years. The search for exoplanets and the study of their systems have revealed the universality of these interconnected processes. While each system is unique, the underlying principles of planetary formation and evolution appear consistent across the galaxy. The diversity of exoplanets, from tightly packed super-Earths to widely spaced gas giants, reflects the intricate interplay of initial conditions, migration, and dynamical interactions. Advanced models and simulations have been instrumental in uncovering these connections, revealing how small changes in one part of a system can cascade into significant differences in its final configuration. For instance, a slight variation in the mass of a protoplanetary disk can determine whether a system forms gas giants or remains dominated by smaller, rocky planets. Similarly, the timing of planetary migration can influence the delivery of water to habitable zones, shaping the potential for life. The interconnectedness of planetary formation also extends to its observational and theoretical foundations. Every new discovery, whether it's a gap in a protoplanetary disk, a new class of exoplanet, or the detection of complex organics on a comet, adds a piece to the puzzle. These observations inform models, which in turn guide future explorations, creating a continuous cycle of learning and discovery. This cosmic interconnection underscores the universality of planetary formation. Whether in our solar system or a distant exoplanetary system, the processes that shape planets are governed by the same physical laws and influenced by similar interactions. By studying these connections, we not only deepen our understanding of individual systems, but also uncover the fundamental principles that govern the cosmos. As we continue to explore and model the universe, the interconnected nature of planetary formation reminds us that our place in the cosmos is part of a larger narrative. The same processes that shaped Earth and its neighbors are at work across the galaxy, creating a diversity of worlds that reflect the creativity and complexity of the universe. In this grand cosmic story, every planet, moon, and star is a chapter, and each new discovery brings us closer to understanding the whole. The story of planetary origins begins in vast, cold regions of interstellar space, where molecular clouds drift silently through the galaxy. These clouds, composed primarily of hydrogen and helium with traces of heavier elements, represent the raw materials from which stars and planetary systems form. Within these clouds, small disturbances, caused by nearby supernovae or gravitational instabilities, trigger the collapse of regions under their own gravity. As these regions condense, they fragment into clumps, each of which may give rise to a new star system. The collapsing material forms a rotating protostellar core surrounded by a flattened disk of gas and dust, the protoplanetary disk. This disk is where planets are born, and its structure is critical in determining the outcome of planetary formation. Closer to the star, the intense heat vaporizes volatile compounds, leaving behind only refractory materials like metals and silicates. These conditions favor the formation of small, rocky worlds. Farther out, where the disk is cooler, water and other volatiles freeze into ices, providing the building blocks for gas and ice giants. This temperature gradient establishes zones within the disk, each fostering different types of planets. At the same time, the star's metallicity, the proportion of elements heavier than helium, determines the abundance of solid materials available for planet formation. Stars with higher metallicity have disks rich in these materials, which accelerates the growth of planets, particularly gas giants. The transformation from dust to planets begins at the microscopic scale, with tiny grains of silicate and ice drifting within the disk. These particles collide and stick together, forming larger aggregates through a process known as coagulation. Initially held together by electrostatic forces, these aggregates grow into pebbles and, eventually, meter-sized objects. However, at this stage, these larger bodies face a significant challenge. The gas in the disk exerts drag, causing them to lose angular momentum and spiral toward the star. This phenomenon, known as the meter-sized barrier, threatens to halt planet formation. To overcome it, certain regions of the disk act as pressure traps, where gas and dust accumulate, allowing particles to grow rapidly into kilometer-sized planetesimals. Streaming instabilities, where interactions between gas and dust create dense filaments, also play a key role in concentrating material for planetesimal formation. Once planetesimals form, gravity becomes the dominant force driving growth. These small bodies collide and merge, creating larger protoplanets in a process known as accretion. In regions beyond the frost line, where icy materials are abundant, protoplanets can grow rapidly into massive cores. If these cores reach a critical mass, they begin to attract and retain gas from the surrounding disk, forming the thick atmospheres of gas giants. This core accretion model explains the formation of most planets, but in certain cases, particularly in massive disks, gravitational instabilities can create dense clumps of gas that collapse directly into giant planets. This alternative pathway, known as disk instability, bypasses the need for a solid core and accounts for the rapid formation of massive planets in systems with short-lived disks. As planets grow, they interact with their surrounding disk, altering its structure and their own orbits. These interactions create density waves in the disk, which exert torques on the planets, causing them to migrate. Smaller planets tend to migrate rapidly inward, while larger planets, which clear gaps in the disk, migrate more slowly. This process, known as planetary migration, explains phenomena like hot Jupiters, gas giants that orbit perilously close to their stars. Migration can also destabilize other bodies in the disk, scattering material and influencing the formation of terrestrial planets. Planets are not solitary. They are often accompanied by moons, rings, and smaller bodies like asteroids and comets. Moons form in several ways. They can coalesce from debris disks around planets, be captured from elsewhere in the system, or result from massive impacts. For example, Earth's moon is thought to have formed when a Mars-sized body collided with the early Earth, ejecting debris that later coalesced into the moon. Moons influence their host planets in profound ways, stabilizing axial tilts, driving tidal heating, and even contributing to habitability. Rings, on the other hand, are often transient features, formed from the remnants of destroyed moons or captured bodies. These structures, though short-lived on cosmic timescales, reveal the dynamic interactions within planetary systems. Smaller bodies, such as asteroids and comets, are relics of the early solar system, preserving the materials and conditions from which planets formed. Asteroids, composed primarily of rock and metal, reflect the inner solar system's composition, while comets, rich in ices and organic compounds, originate from the colder, outer regions. These bodies play a crucial role in planetary systems, delivering water and organics to terrestrial planets and influencing the evolution of atmospheres and climates. The chemical composition of planets and their atmospheres provides a window into their formation histories. Within the disk, the abundance and distribution of elements vary with distance from the star, creating chemically distinct regions. For instance, Rocky planets in the inner disk are rich in silicates and metals, while outer planets incorporate more ices and gases. Variations in the carbon-to-oxygen ratio, as well as the availability of heavy elements, influence the bulk composition and potential habitability of planets. Water, carbon, nitrogen, and other elements essential for life are distributed unevenly, with their delivery to planets often mediated by asteroids and comets. The conditions necessary for habitability extend beyond the presence of water. Stable climates, magnetic fields, and plate tectonics all contribute to creating environments where life can thrive. Magnetic fields, generated by a planet's molten core, protect the atmosphere from solar wind and radiation. Plate tectonics regulate the carbon cycle, balancing greenhouse gases and stabilizing surface temperatures. While Earth exemplifies these conditions, other worlds, such as Europa and Titan, demonstrate that life may emerge in diverse environments, including subsurface oceans or exotic chemistries. Our solar system provides a blueprint for understanding planetary formation. The migration of Jupiter and Saturn, the asteroid belt's role as a failed planet, and the delivery of water to Earth by comets all highlight the interconnected processes shaping planetary systems. Studying these phenomena in the context of exoplanetary systems reveals both the uniqueness and universality of our solar system's history. Exoplanet discoveries continue to challenge and refine our understanding of planetary diversity. Observations reveal tightly packed systems, super-Earths, and mini-Neptunes, none of which exist in our solar system. These findings suggest that the processes shaping planetary systems are highly sensitive to initial conditions, such as the mass and metallicity of the protoplanetary disk. Advances in observational technology and simulations are driving the field forward. Instruments like the James Webb Space Telescope and ground-based observatories are uncovering the atmospheric compositions of exoplanets, while simulations recreate the conditions of planet-forming disks and test hypotheses about migration and stability. These tools are not only deepening our understanding of planetary formation, but also guiding the search for habitable worlds and extraterrestrial life. The processes that give rise to planets are deeply interconnected, governed by universal principles that apply across the cosmos. From the formation of stars to the emergence of life, each stage in this cosmic journey builds upon the last, creating a rich and dynamic web of interactions. By studying these processes, we gain not only a deeper understanding of our own origins, but also a glimpse into the vast diversity of worlds that populate the universe. The interconnected processes of planetary formation underscore the universal nature of these phenomena, linking the life cycles of stars, the dynamics of disks, and the eventual creation of planetary systems in ways that transcend individual systems. Every stage of planetary formation contributes to the structure, composition, and evolution of worlds, weaving a continuous narrative from the microscopic to the monumental. One of the most remarkable aspects of planetary formation is the interplay between the early chaotic stages of star and planet formation and the long-term stability or instability of mature planetary systems. The protoplanetary disk, far from being a calm and uniform environment, is a turbulent and dynamic stage where particles collide, coalesce, and grow against a backdrop of swirling gas and shifting pressures. The localized concentration of material in regions like pressure bumps or eddies acts as a crucible for the formation of planetesimals, while gravitational instabilities can initiate rapid collapse into massive structures. These early interactions set the stage for the kinds of planets that will emerge and where they will reside. As planets begin to form, their growth is not an isolated process but one that influences and is influenced by the surrounding environment. For example, a growing protoplanet's gravitational pull creates ripples in the disk, which can either accelerate its growth by attracting more material or slow it down by depleting the local supply of dust and gas. These interactions are not only pivotal in shaping individual planets, but also in determining the overall distribution of material within the disk, which influences the formation of additional planets. The gravitational interplay between forming planets is another layer of this interconnected process. Early on, these interactions can result in resonances, where planets settle into stable orbital relationships that persist for billions of years. However, they can also lead to instability, scattering planets into highly eccentric orbits or ejecting them entirely from the system. Such dynamics are believed to explain the prevalence of free-floating planets, worlds that roam the galaxy untethered to any star. Even after a planetary system reaches a relatively stable configuration, the interconnectedness of its components remains crucial. Moons, for example, often have significant impacts on their host planets. Earth's moon stabilizes its axial tilt, moderating seasonal variations and creating conditions favorable for life. Tidal interactions between a planet and its moons, or between moons themselves, can generate heat, as seen on Io, Europa, and Enceladus. This heat drives geological and potentially biological activity, highlighting the importance of these secondary bodies in shaping the habitability of planets. Rings, while often temporary features, provide further evidence of the dynamic relationships within planetary systems. These structures form and evolve through interactions with moons, debris, and the planet's gravitational field. Saturn's rings, though iconic, are thought to be relatively young, possibly the result of a destroyed moon or a captured comet. Similar processes may be at work in exoplanetary systems, creating transient features that reflect the ongoing dynamism of planetary systems. Smaller bodies, such as asteroids and comets, serve as reservoirs of primitive material and agents of change within planetary systems. These objects not only preserve the chemical signatures of the early solar system, but also act as delivery mechanisms for water and organic compounds to terrestrial planets. Impact events, while potentially catastrophic, can also introduce essential materials that contribute to the emergence of life. The Late Heavy Bombardment, a period of intense asteroid and comet impacts in the solar system's history, may have played a key role in shaping the environments of Earth and other inner planets. The chemical composition of planets and their atmospheres provides a critical link between the conditions of their formation and their potential for life. Atmospheric evolution is a dynamic process influenced by factors such as volcanic outgassing, impacts, and the escape of lighter gases into space. These processes are shaped by a planet's size, composition, and proximity to its star. For example, Earth's atmosphere has been continuously modified by life itself, which introduced oxygen through photosynthesis. This interplay between life and its environment underscores the interconnectedness of biological and planetary processes. In exoplanetary systems, observations of diverse atmospheric compositions highlight the role of chemical evolution in shaping planetary diversity. From hot Jupiters with atmospheres dominated by exotic compounds to temperate worlds with signs of water vapor, these discoveries reveal the vast range of possible outcomes in planetary evolution. Understanding these atmospheres also helps us refine models of habitability, as the presence of certain gases can indicate conditions favorable for life. The search for life beyond Earth is perhaps the most compelling reason for studying planetary systems. Habitability depends on a complex interplay of factors, including a planet's size, distance from its star, atmospheric composition, and geological activity. However, life's emergence and persistence may also depend on chance events, such as the delivery of water or the presence of a stabilizing moon. By studying these processes in the context of our solar system and beyond, scientists are uncovering the delicate balance required to create and sustain habitable environments. Advanced observational tools and computational models are driving this exploration forward. Instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope are providing unprecedented detail about exoplanetary atmospheres, protoplanetary disks, and the physical conditions of distant worlds. Meanwhile, high-resolution simulations are recreating the chaotic environments of forming planetary systems, testing hypotheses about migration, disk dynamics, and the role of chemical gradients in shaping planetary compositions. The interconnectedness of planetary formation is not only a physical reality, but also a conceptual framework for understanding the universe. From the recycling of elements in stars to the emergence of life on planets, each stage of this process builds on the last, creating a continuum that spans time and space. This perspective transforms our view of planetary systems from isolated phenomena to integral parts of a larger cosmic ecosystem. As our understanding of planetary formation deepens, we are reminded that the processes that shaped Earth and its neighbors are not unique, but part of a universal story. The diversity of worlds observed in the galaxy reflects the creativity and complexity of these processes, offering endless opportunities for discovery. Each new finding, whether it's a habitable zone planet, an icy moon with a subsurface ocean, or an atmosphere rich in exotic compounds, adds a new chapter to this ongoing narrative, bringing us closer to answering some of humanity's oldest questions. How do planets form? What makes a world habitable? And are we alone in the universe? The search for answers to these profound questions extends beyond observation and modeling to the direct exploration of our solar system and beyond. Missions to planets, moons, asteroids, and comets are crucial for uncovering the processes that govern planetary formation and evolution. By examining these celestial bodies up close, we gain insights into the materials and mechanisms that shaped not only our solar system, but also the countless others scattered across the galaxy. Mars has long been a focus of exploration due to its potential to reveal clues about planetary habitability and the history of water in the inner solar system. Robotic missions like Perseverance and Curiosity have uncovered evidence of ancient rivers, lakes, and possibly even oceans, suggesting that Mars was once a warm and wet planet capable of supporting life. These findings highlight the dynamic nature of planetary climates and the factors that lead to the loss of habitability over time. Future missions, including sample return efforts, will allow scientists to analyze Martian materials with unprecedented precision, searching for biosignatures or traces of ancient microbial life. Beyond Mars, the icy moons of the outer solar system have emerged as prime targets for astrobiological research. Europa, one of Jupiter's largest moons, harbors a vast subsurface ocean beneath its icy crust. This ocean, warmed by tidal heating, contains the necessary ingredients for life, including water, energy sources, and potentially organic compounds. The upcoming Europa Clipper mission will investigate the moon's surface and search for signs of habitability, including the composition of water plumes that may erupt from its interior. Similarly, Enceladus, a small moon of Saturn, has captivated scientists with its active geysers that spew water vapor, ice, and organic molecules into space. These plumes provide a direct link to the moon's subsurface ocean, allowing researchers to study its chemistry without the need to drill through the icy shell. Enceladus represents one of the most accessible targets in the search for extraterrestrial life, with its potential biosphere offering tantalizing possibilities. Titan, Saturn's largest moon, is another unique world that defies traditional notions of habitability. With its thick atmosphere and lakes of liquid methane and ethane, Titan is a cold but chemically rich environment. The Dragonfly mission, set to launch in the 2030s, will explore Titan's surface and atmosphere, searching for prebiotic chemistry and studying how complex organic molecules form and evolve in such an alien environment. Titan's unusual conditions may hold clues to how life could arise under radically different circumstances from those on Earth. Asteroids and comets, often viewed as the leftover debris of planetary formation, play a critical role in understanding the building blocks of planets. Missions like OSIRIS-RX and Hayabusa-2 have returned samples from asteroids Bennu and Ryugu, providing invaluable data about their composition and structure. These primitive bodies contain the raw materials that contributed to the formation of planets and the delivery of water and organics to the inner solar system. By studying them, scientists can trace the pathways that led to the emergence of habitable worlds. The study of exoplanets continues to expand our understanding of planetary systems, revealing a staggering diversity of worlds and challenging assumptions based on our solar system. Super-Earths, mini-Neptunes, and hot Jupiters dominate the exoplanetary landscape, showcasing the wide range of outcomes produced by planetary formation. Observations of Earth-sized planets in habitable zones, such as those in the TRAPPIST-1 system, highlight the potential for life beyond our solar system, while atmospheric studies provide insights into the conditions on these distant worlds. Future telescopes, such as the Roman Space Telescope and the Extremely Large Telescope, will revolutionize our ability to study exoplanets, particularly their atmospheres. By detecting molecules like water vapor, methane, and oxygen, these instruments will help identify potentially habitable planets and investigate the chemical processes that shape their environments. Direct imaging techniques will allow scientists to observe planets and moons in detail, providing new opportunities to study their surfaces, climates, and potential for life. The integration of artificial intelligence and machine learning into planetary science is accelerating discoveries and refining models. These tools are particularly valuable for analyzing the vast datasets generated by telescopes and simulations, identifying patterns and anomalies that might otherwise go unnoticed. AI-driven approaches are helping researchers optimize mission planning, simulate complex systems, and explore the intricate interactions within planetary systems. The study of planetary formation is not only about understanding how worlds come into being, but also about placing humanity within the broader context of the universe. Each discovery, whether it is a distant exoplanet with a peculiar atmosphere or an ancient asteroid with water-rich minerals, adds a piece to the puzzle of our cosmic origins. By uncovering the processes that link stars, disks, and planets, we come closer to understanding the conditions that make life possible and the likelihood of finding it elsewhere. As we continue to explore, observe, and model, the interconnectedness of planetary formation becomes increasingly clear. The same principles that govern the behavior of protoplanetary disks and the assembly of planets also shape the evolution of their climates, the dynamics of their moons, and the potential for life. This holistic view transforms planetary science into a discipline that is as much about understanding the universe as it is about understanding ourselves. The journey from dust to life is a testament to the complexity and creativity of the cosmos. From the first grains of dust in a protoplanetary disk to the emergence of intelligent life capable of pondering its origins, this process is a continuous thread that connects all worlds, known and unknown. As we push the boundaries of exploration and discovery, we are reminded that the story of planetary formation is far from over. Each new mission, observation, and model brings us closer to unraveling the mysteries of the universe and finding our place within its vast expanse. The next chapters of planetary science are being written not only by new discoveries, but also by the profound questions that remain unanswered. These mysteries drive the design of future missions, the development of advanced models, and the construction of ever more sophisticated telescopes. As humanity seeks to understand how planets form, evolve, and support life, the scientific journey becomes increasingly multidisciplinary, drawing from astrophysics, geology, chemistry, and biology to paint a fuller picture of the cosmos. The search for habitable worlds beyond our solar system is perhaps the most captivating frontier. As instruments like the James Webb Space Telescope begin to probe the atmospheres of distant exoplanets, scientists are honing their ability to detect biosignatures, chemical markers that may indicate the presence of life. Molecules such as oxygen, ozone, methane, and nitrous oxide, when found together in specific ratios, could point to biological processes. However, interpreting these signals requires a nuanced understanding of planetary atmospheres, geology, and potential abiotic processes that could mimic life. This challenge underscores the interconnected nature of planetary science and the need for multidisciplinary approaches. In the solar system, the exploration of icy moons continues to offer tantalizing prospects for finding extraterrestrial life. Europa's subsurface ocean, shielded by a thick ice crust, is a prime candidate. The Europa Clipper mission will focus on understanding the moon's ice shell, potential water plumes, and the chemistry of its surface, which may harbor materials from the ocean below. If organic compounds or chemical energy sources like hydrogen and sulfates are detected, it would strengthen the case for habitability. Enceladus presents another exciting target. The detection of organic molecules in its plumes suggests that its subsurface ocean contains the ingredients necessary for life. Future missions could analyze these plumes in greater detail or deploy probes capable of penetrating the ice to directly sample the ocean. These missions would not only address questions about habitability, but also test the limits of life's adaptability in extreme environments. Titan's exotic chemistry and methane lakes push the boundaries of what we consider habitable. The Dragonfly mission will explore Titan's surface and atmosphere, searching for prebiotic molecules and studying the interactions between its organic-rich environment and liquid methane. By understanding Titan, scientists hope to expand the concept of habitability to worlds vastly different from Earth, where life might arise under completely alien conditions. Mars remains a cornerstone of astrobiological research. While the planet's surface is harsh and arid today, evidence of ancient riverbeds, lake basins, and mineral deposits indicates a warmer and wetter past. Missions like Perseverance are not only searching for signs of ancient microbial life, but also preparing for the return of Martian samples to Earth. These samples could provide definitive answers about Mars's potential for hosting life in its distant past and reveal more about the processes that led to its current state. Asteroids and comets continue to be vital to understanding planetary formation and the delivery of life's building blocks. Missions like OSIRIS-RX and Hayabusa 2 have demonstrated the feasibility of returning samples from these small bodies, and future missions may focus on comets rich in volatile ices and organics. These primitive bodies are time capsules, preserving the conditions of the early solar system and offering clues about how water and complex molecules were delivered to Earth and other planets. Exoplanet research is redefining our understanding of planetary diversity. The discovery of thousands of exoplanets has revealed worlds that defy traditional classification, such as lava planets with molten surfaces, super-Earths with thick atmospheres, and mini-Neptunes that blur the line between rocky and gaseous planets. Each of these discoveries challenges existing models of planetary formation and highlights the need for more comprehensive theories that can account for the wide range of observed outcomes. The study of planetary atmospheres is a particularly exciting area of growth. Instruments like JWST, TESS, and upcoming ground-based observatories are beginning to resolve the compositions, temperatures, and dynamics of exoplanetary atmospheres. These observations provide critical insights into how planets interact with their stars and how their atmospheres evolve over time. Understanding these processes is essential for identifying planets that might support life and distinguishing habitable worlds from those that are merely Earth-like in size or location. Simulations and advanced computational models are also playing a transformative role. By recreating the conditions of protoplanetary disks, scientists can test hypotheses about the formation of planetesimals, the migration of gas giants, and the assembly of terrestrial planets. These models incorporate increasingly detailed physics and chemistry, allowing researchers to explore phenomena such as the role of magnetic fields in disk evolution or the effects of stellar radiation on atmospheric escape. Machine learning is further enhancing these efforts, enabling the analysis of massive datasets and the identification of subtle patterns in planetary systems. The search for exomoons represents another emerging frontier. Moons are critical to understanding planetary systems, influencing their dynamics, climates, and potential for life. While detecting moons around exoplanets remains challenging, advancements in direct imaging and transit techniques may soon make it possible. If exomoons are found, they could provide additional habitats for life, particularly if they orbit giant planets in habitable zones or possess subsurface oceans heated by tidal forces. As we continue to push the boundaries of exploration, the interconnected nature of planetary systems becomes ever more apparent. Every discovery, whether it's a distant exoplanet with a peculiar orbit or an asteroid rich in organic compounds, adds to the larger narrative of how planets form, evolve, and influence their surroundings. These findings not only deepen our understanding of the cosmos, but also offer profound insights into our own origins and the factors that make Earth a unique, life-supporting world. Ultimately, the study of planetary formation is about more than understanding worlds beyond our own. It's about connecting the dots in the grand cosmic tapestry. Each planet, moon, and star is a thread in this tapestry, woven together by the universal processes of gravity, chemistry, and time. As we unravel these threads, we are reminded of our place in the universe, part of a vast and intricate web of creation that stretches across space and time. The future of planetary science is as much about asking new questions as it is about finding answers. What conditions lead to the emergence of life? How common are habitable worlds in the galaxy? And what does the diversity of planetary systems tell us about the processes that shaped our own solar system? Each new discovery brings us closer to answering these questions while sparking new mysteries to explore. As we continue to look outward, we are also looking inward, searching for a deeper understanding of the cosmos and our place within it. The story of planetary formation is a continuous saga of discovery, each chapter revealing new complexities and raising profound questions about the universe. This pursuit connects the smallest particles of cosmic dust to the grandest scales of interstellar dynamics, forming a cohesive narrative that ties together the birth of stars, the evolution of planets, and the emergence of life. As we expand our reach into the cosmos, this narrative grows richer, informed by new technologies, interdisciplinary collaboration, and the collective curiosity of humanity. In the earliest stages of a planetary system, the interaction between gravity and angular momentum shapes the protoplanetary disk, setting the stage for the creation of planets. This environment, dynamic and turbulent, fosters the rapid growth of planetesimals through processes that are both chaotic and ordered. Dust grains collide and stick, overcoming barriers that would otherwise prevent their growth, while the forces within the disk sculpt regions where material accumulates, accelerating the transition from dust to larger bodies. These early processes are deeply connected to the broader environment of star formation. The metallicity of the star dictates the abundance of heavy elements available in the disk, influencing not only the types of planets that can form, but also their potential for habitability. High metallicity systems tend to produce gas giants and larger terrestrial planets, while lower metallicity disks may favor smaller, rocky worlds. These relationships underline the importance of cosmic recycling, as the elements forged in previous generations of stars become the building blocks of new planetary systems. Once planetesimals form, gravity takes center stage, driving the accretion of larger bodies and the differentiation of planetary interiors. Protoplanets emerge, competing for resources and interacting with the disk and one another in a gravitational dance that shapes their orbits and distributions. Migration, a critical process in this stage, redefines the architecture of the system, bringing planets closer to or farther from their star. This movement not only determines the final locations of planets, but also influences the distribution of materials, such as water and volatiles, which are crucial for habitability. The influence of migration and gravitational interactions extends beyond individual planets to the entire system. These processes explain the prevalence of phenomena like hot Jupiters, tightly packed exoplanetary systems, and eccentric orbits, each a testament to the dynamism of planetary systems. The interactions between planets, disks, and other bodies create a feedback loop, where small changes in one component can have cascading effects, shaping the system's evolution over millions or billions of years. The role of moons, rings, and smaller bodies within planetary systems is equally significant. Moons, whether formed through co-accretion, capture, or giant impacts, influence their host planets in profound ways. They stabilize axial tilts, drive tidal heating, and, in some cases, create conditions conducive to life. Rings, often temporary but striking features, provide insights into the processes of tidal disruption and gravitational sculpting. Smaller bodies, such as asteroids and comets, act as time capsules, preserving the conditions of the early solar system and delivering essential materials to planets, including water and organic molecules. Chemical diversity within protoplanetary disks further highlights the interconnected nature of planetary formation. The gradients in temperature and composition within the disk determine the types of planets that form and their potential for hosting life. For instance, the distribution of water, carbon, and nitrogen plays a critical role in defining habitability. These elements, distributed by the dynamics of the disk and later by impacts, create the chemical foundations for life. Understanding these processes not only sheds light on our own origins, but also guides the search for life elsewhere. The study of exoplanets has expanded our understanding of planetary diversity, challenging traditional models and revealing new possibilities. Super-Earths, mini-Neptunes, and lava worlds, none of which exist in our solar system, highlight the range of outcomes produced by planetary formation. These discoveries have forced scientists to revisit assumptions about what constitutes a typical planetary system, revealing the immense variety of pathways that lead to the creation of worlds. Advanced telescopes and space missions are at the forefront of these discoveries, offering unprecedented views of distant planets and their systems. The James Webb Space Telescope, with its ability to analyze atmospheric compositions, is poised to revolutionize our understanding of exoplanetary environments, searching for biosignatures and probing the conditions of potentially habitable worlds. Meanwhile, missions like Europa Clipper, Dragonfly, and Mars Sample Return are exploring the solar system's most promising sites for life, from subsurface oceans to ancient riverbeds. Simulations and computational models play a complementary role, allowing scientists to recreate the conditions of planetary systems and test hypotheses about their formation and evolution. These tools, enhanced by machine learning and artificial intelligence, provide insights into processes that are difficult or impossible to observe directly. By integrating data from observations and simulations, scientists are building a more comprehensive picture of how planets form and evolve. The interconnectedness of planetary formation is perhaps most evident in the search for life. The emergence of life depends on a delicate interplay of factors, including a planet's composition, location, atmosphere, and geological activity. These factors, in turn, are shaped by the processes that govern the formation of stars, disks, and planets. This interconnected narrative underscores the universality of the forces that create habitable worlds, linking the origins of life on Earth to the potential for life elsewhere. As we continue to explore the cosmos, the story of planetary formation becomes increasingly rich and complex. Each new discovery, whether it's a distant exoplanet with a unique atmosphere or an icy moon with evidence of subsurface oceans, adds a new dimension to our understanding of the universe. These discoveries remind us that planetary systems are not isolated phenomena, but integral parts of a larger cosmic web, shaped by the same forces that govern stars, galaxies, and the universe itself. The future of planetary science lies in its ability to address the profound questions that have captivated humanity for centuries. How common are Earth-like planets? What conditions are necessary for life? And are we alone in the universe? Each step forward brings us closer to answering these questions, while simultaneously revealing new mysteries to explore. In this journey, the study of planetary formation is not just about understanding the cosmos. It is about finding our place within it. The study of planetary formation is an ever-expanding journey into the depths of cosmic evolution, revealing the intricate processes that sculpt planets, moons, and entire star systems. As we delve further into this field, we uncover connections that link the formation of worlds to the life cycles of stars, the dynamics of galaxies, and the conditions that foster life. Each discovery adds a new thread to the cosmic tapestry, enriching our understanding of the universe and our place within it. The earliest stages of planetary formation are marked by the collapse of molecular clouds, regions of interstellar gas and dust that condense under their own gravity. These collapses form protostars surrounded by rotating disks of gas and dust, the cradles of planets. The dynamics within these disks, shaped by gravity, temperature gradients, and magnetic fields, create distinct regions where different types of planets can form. Closer to the star, where temperatures are high, rocky planets emerge from refractory materials like silicates and metals. Farther out, in the cooler regions beyond the frost line, ices dominate, providing the building blocks for gas and ice giants. This distribution of materials within protoplanetary disks is not random. It reflects the influence of the central star's metallicity and the turbulence within the disk. High metallicity stars, rich in elements heavier than helium, tend to produce disks with greater densities of solids, accelerating the growth of planetesimals and facilitating the formation of massive planets. The interactions between dust, gas, and magnetic fields further shape the disk, creating zones of enhanced density where material accumulates, leading to the formation of the first solid bodies. As dust grains collide and stick together, they grow into larger aggregates through a process known as coagulation. This growth faces challenges, such as the meter-size barrier, where drag from the surrounding gas causes larger particles to spiral inward toward the star. However, mechanisms like pressure traps and streaming instabilities allow material to bypass this barrier, forming kilometer-sized planetesimals that serve as the seeds for planetary growth. These early processes highlight the delicate balance of forces required to transition from dust to solid worlds. The emergence of planetesimals marks a turning point in planetary formation, as gravity begins to dominate the process. These small bodies collide and merge, forming larger protoplanets in a dynamic and competitive environment. In the inner disk, where rocky materials prevail, these collisions produce the terrestrial planets. In the outer disk, where ices and gas are abundant, protoplanets can grow into massive cores capable of accreting thick gaseous envelopes, giving rise to gas and ice giants. The growth of these planets is not a solitary process. As they interact with the surrounding disk, they create waves and gaps that influence their own migration and the distribution of material within the disk. This migration can bring planets closer to or farther from their star, reshaping the architecture of the system. The presence of hot Jupiters, gas giants orbiting extremely close to their stars, illustrates the dramatic effects of migration, as these planets likely form farther out before spiraling inward. The interplay between planets and their disks extends to the formation of moons and rings. Moons, whether co-accreted, captured, or formed from collision debris, are integral to the dynamics of planetary systems. They stabilize the tilts of their host planets, drive tidal heating, and influence the behavior of rings and smaller bodies. Rings, often composed of ice and rock, are dynamic systems sculpted by the gravitational forces of planets and their moons, offering a window into the processes of tidal disruption and accretion. Smaller bodies like asteroids and comets serve as both relics of the early solar system and agents of change. These objects preserve the chemical signatures of the disk from which they formed, providing a record of the conditions that existed during the earliest stages of planetary formation. Their impacts on planets deliver essential materials, such as water and organic compounds, that contribute to the development of habitable environments. The late heavy bombardment, a period of intense impacts in the early solar system, likely played a crucial role in shaping the conditions for life on Earth. The chemical diversity of planets reflects the gradients within the protoplanetary disk and the processes that govern their evolution. The compositions of atmospheres and surfaces are shaped by initial conditions, migration, and later interactions with other bodies. The delivery of volatiles and organics by comets and asteroids further enriches planetary environments, creating the chemical foundations for life. Understanding these processes is critical for identifying planets that may be habitable and for interpreting the signatures of life in distant systems. The discovery of exoplanets has expanded the scope of planetary science, revealing a diversity of worlds far beyond what was once imagined. Super-Earths, mini-Neptunes, and tightly packed multi-planet systems challenge traditional models and highlight the need for new theories that can account for their formation. Observations of these planets and their atmospheres provide critical data for understanding the range of outcomes produced by planetary formation. Advances in observational technology are driving these discoveries. Telescopes like the James Webb Space Telescope and the Extremely Large Telescope are enabling detailed studies of exoplanetary atmospheres, searching for signs of water, methane, oxygen, and other potential biosignatures. These instruments are also revealing the structures of protoplanetary disks, providing direct evidence of the processes that give rise to planets. Simulations and computational models are complementing these observations, offering insights into the dynamics of planetary systems. These models recreate the conditions of protoplanetary disks, test hypotheses about migration and instability, and predict the outcomes of complex interactions. By integrating data from multiple disciplines, these tools are building a more complete picture of how planets form and evolve. The search for life drives much of this research, linking planetary formation to the broader quest to understand our place in the universe. Habitability depends on a complex interplay of factors, from the delivery of water and organics to the presence of stable climates and protective magnetic fields. These factors, in turn, are shaped by the processes of planetary formation and evolution. The discovery of potentially habitable worlds, whether within our solar system or among the stars, brings us closer to answering the profound question of whether we are alone. As we continue to explore the cosmos, the interconnectedness of planetary formation becomes increasingly clear. Every discovery, from a distant exoplanet with an exotic atmosphere to an asteroid rich in water ice, adds a piece to the puzzle of our origins. This narrative, spanning billions of years and countless systems, reminds us that the forces shaping the universe are universal, connecting the smallest grains of dust to the grandest structures in the cosmos. The future of planetary science lies in its ability to address both fundamental questions and unexpected discoveries. How do planets form in environments vastly different from our own? What are the conditions that lead to the emergence of life? And what does the diversity of planetary systems tell us about the processes that shaped our solar system? Each step forward brings us closer to answering these questions while unveiling new mysteries to explore. In this pursuit, the study of planetary formation is not just about understanding the cosmos. It is about understanding ourselves and our place in the universe. The interconnected processes of planetary formation not only reveal the mechanisms that give rise to worlds, but also offer profound insights into the broader dynamics of the universe. These processes, universal in their application, connect the smallest particles of cosmic matter to the grandest scales of celestial organization, shaping not only planets, but also the conditions necessary for life itself. As we unravel these mysteries, we are drawn into a narrative that spans billions of years, linking the origins of stars and galaxies to the emergence of habitable worlds. The earliest moments of planetary formation are born in the vast molecular clouds that serve as stellar nurseries. These cold, dense regions of space harbor the raw materials for stars and their planetary systems. When regions within these clouds collapse under their own gravity, they form protostars surrounded by rotating disks of gas and dust. These disks, chaotic and dynamic, are the cradles of planets, where the interplay of temperature, pressure, and turbulence sculpts the diversity of planetary systems. The composition of these disks reflects the metallicity of their parent stars, a measure of the abundance of elements heavier than helium. Stars rich in metals tend to produce disks with more solid material, fostering the rapid formation of planetesimals and accelerating the growth of giant planets. These relationships highlight the role of stellar evolution in shaping the environments that lead to planet formation, linking the life cycles of stars to the creation of worlds. Within the disk, dust grains collide and stick together, forming larger aggregates through a process known as coagulation. These collisions, though seemingly simple, are governed by complex physical forces that allow particles to overcome barriers like fragmentation and radial drift. As these aggregates grow into pebbles and then meter-sized objects, they face significant challenges, such as gas drag that pulls them inward toward the star. However, localized phenomena like pressure bumps and streaming instabilities create regions where material can accumulate, bypassing these barriers and enabling the formation of kilometer-sized planetesimals. The formation of planetesimals marks the beginning of gravity's dominant role in planetary formation. These small bodies collide and merge, creating protoplanets that compete for material within the disk. In the inner regions, where rocky materials dominate, these collisions produce terrestrial planets. Farther out, where ices are abundant, protoplanets grow into massive cores that attract and retain gaseous envelopes, forming the gas and ice giants. These giants, with their immense gravitational influence, shape the architecture of their systems, scattering smaller bodies and influencing the formation of moons, asteroids, and comets. The interactions between growing planets and their surrounding disks create waves and gaps that drive planetary migration, a process that reshapes the layout of the system. This migration explains phenomena like hot Jupiters, gas giants that orbit close to their stars despite having formed much farther out. Migration also plays a critical role in delivering water and volatiles to the inner planets, influencing their potential for habitability. The movement of planets within the disk is a dynamic and often chaotic process, demonstrating the interconnected nature of planetary formation. Moons and rings, though often seen as secondary features, are integral to the dynamics of planetary systems. Moons can stabilize the axial tilts of their host planets, influence tides, and drive geological activity through tidal heating. Rings, composed of ice and rock, offer insights into processes like tidal disruption and accretion. These features are not static. They evolve over time, shaped by the gravitational interactions between planets, moons, and smaller bodies. Asteroids and comets, remnants of the early solar system, serve as both witnesses and participants in planetary formation. These small bodies preserve the chemical and physical conditions of the protoplanetary disk, offering a glimpse into the processes that shaped the solar system. Their impacts on planets deliver water and organic compounds, essential ingredients for life. The role of these impacts in shaping planetary environments underscores the interconnectedness of planetary formation and habitability. The chemical diversity of planets and their atmospheres reflects the conditions of their formation and evolution. The composition of a planet's atmosphere is influenced by its initial materials, geological activity, and interactions with its star. Volcanic outgassing, impacts, and atmospheric escape all contribute to the dynamic evolution of atmospheres, shaping the conditions on a planet's surface. Understanding these processes is crucial for identifying planets that may harbor life and interpreting the signatures of habitability. The discovery of exoplanets has revolutionized our understanding of planetary systems, revealing a staggering diversity of worlds. From lava planets with molten surfaces to super-Earths and mini-Neptunes, these discoveries challenge traditional models and expand the possibilities for planetary formation. Observations of exoplanetary atmospheres provide critical data for understanding their climates, compositions, and potential for life, offering a window into the conditions that exist on distant worlds. Advances in technology, particularly the development of powerful telescopes like the James Webb Space Telescope and the Extremely Large Telescope, are enabling unprecedented studies of exoplanets and their systems. These instruments are capable of analyzing the atmospheric compositions of distant planets, detecting molecules like water vapor, methane, and oxygen that could indicate habitability. By observing protoplanetary disks, these telescopes also provide direct evidence of the processes that give rise to planets, offering new insights into the earliest stages of planetary formation. Simulations and computational models complement these observations, allowing scientists to recreate the conditions of protoplanetary disks and test hypotheses about planetary dynamics. These models, enhanced by machine learning, are capable of analyzing vast data sets and uncovering patterns that reveal the underlying principles of planetary formation. By integrating data from observations and simulations, researchers are building a more comprehensive understanding of how planets form and evolve. The search for life is a driving force in planetary science, linking the study of planetary formation to the broader quest to understand our place in the universe. The conditions that make a planet habitable are shaped by the processes of its formation, from the delivery of water and organics to the evolution of its atmosphere and climate. The discovery of potentially habitable worlds, whether within our solar system or among the stars, brings us closer to answering the profound question of whether we are alone. The interconnected nature of planetary formation reveals a universe that is dynamic, creative, and profoundly interwoven. Every discovery, whether it's a distant exoplanet with an unusual orbit or an asteroid rich in organic compounds, adds to our understanding of the cosmos and the processes that shaped our own world. This narrative, spanning billions of years and countless systems, underscores the universality of planetary formation, connecting the smallest particles of dust to the emergence of life. As we continue to explore, observe, and model, the story of planetary formation becomes richer and more complex. Each new finding raises new questions, driving the field forward and expanding our understanding of the universe. In this journey, the study of planetary formation is not just about understanding the cosmos. It is about understanding ourselves and our place within its vast and intricate expanse. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.